Hello there, and welcome to Science for Sleep, where curiosity gets cozy and even the most distant corners of the universe are explored at a pace gentle enough to drift off to. Tonight, we're setting our sights on something that sounds almost impossible at first. Not a planet, not a galaxy, not even a star, but an ocean. And not just any ocean, but the largest one we know of in the entire universe, hidden around a distant object known as APM 08279 plus 5255. Now, when you hear the word ocean, your mind might wander to waves rolling onto a quiet shore, or maybe the deep, dark water stretching far beyond the horizon. But this is something very different. There are no beaches there, no tides, no salty breeze. Instead, this ocean exists in the cold, vast emptiness of space, billions of light years away, surrounding one of the most powerful objects ever observed. Before we get too far into it, though, I'd like to ask you something simple. Where are you listening from right now? And what time is it in your little corner of the world? It's always a bit fascinating, isn't it? The idea that while we're here, sharing this quiet moment together, we're scattered across different cities, countries, maybe even continents, each of us experiencing a slightly different version of the same night. If you find this kind of slow, curious journey relaxing, or just a nice way to unwind at the end of your day, feel free to give the video a like and maybe subscribe. It helps this calm little space reach more people who might need a softer ending to their evening. Now, let's ease into tonight's story. Because somewhere out there, far beyond the stars you can see, beyond even the faintest galaxies visible through powerful telescopes, there is a place where water exists on a scale so large it almost stops making sense. And it all begins with the discovery that, at first, didn't seem like it had anything to do with oceans at all. Astronomers weren't looking for water when they first studied a PM 08279 plus 5255. In fact, when this object was identified, what caught their attention wasn't anything resembling an ocean, but something much brighter, much more intense. It appeared as a quasar. Now that's a word that sounds a little technical, but the idea behind it is surprisingly straightforward. A quasar is essentially the extremely bright center of a distant galaxy, powered by a supermassive black hole. Not the quiet kind you might imagine, simply sitting in space, but one that is actively feeding, pulling in enormous amounts of matter. As gas and dust spiral toward this black hole, they heat up dramatically, glowing with incredible energy. So much so that the light from a quasar can outshine the entire galaxy it lives in. And a PM 08279 plus 5255 is not just any quasar. It's one of the most luminous ever discovered. To put it gently, this is not a calm place. It's a region filled with intense radiation, powerful gravitational forces, and matter moving at astonishing speeds. If Earth's oceans feel vast and deep, this environment is something else entirely. It's more like a storm that never ends, except instead of clouds and rain, it's made of energy, gas, and light. So naturally, finding water there was not exactly what anyone expected. You might assume that water, something so familiar and, in a way, so fragile, would struggle to exist in such extreme conditions. After all, here on Earth, water behaves in very predictable ways. It freezes, it evaporates, it flows gently downhill. But out there, near a quasar, the rules feel a little less intuitive, and yet that's exactly what astronomers found. Not liquid water in the sense we're used to, not waves or droplets, but water in the form of vapor. Enormous clouds of it, spread across a region so large it defies easy comparison. When scientists first detected it, they weren't looking through a telescope in the traditional sense. They were analysing light, or more specifically, the subtle fingerprints that molecules leave behind in that light. Every molecule, including water, interacts with light in a unique way. It absorbs and emits specific wavelengths, creating patterns that can be identified even across unimaginable distances. So, by studying the light coming from this quasar, astronomers began to notice something familiar. A pattern, a signature. one that matched water vapor, and not just a little bit of it. We're talking about a quantity of water that is estimated to be at least 140 trillion times the amount found in all of Earth's oceans combined. Let that settle in for a moment. If you took every ocean on Earth, every drop in the Pacific, the Atlantic, the Indian, the Arctic, and multiplied it again and again until the number barely feels real, you'd begin to approach the scale of what exists around APM 08279 plus 5255. It's not an ocean in the traditional sense, but when something contains that much water, the word starts to feel appropriate. And yet, despite that familiar term, everything about this ocean is different. For one thing, it isn't confined to a surface. There's no boundary where water meets land. Instead, it's spread out in a vast region of space, mixed with gas, influenced by radiation, constantly shifting under the immense gravitational pull of the black hole at the centre. The temperature there is also far from what we'd consider comfortable. While space itself is often cold, the environment near a quasar can be surprisingly warm, at least by cosmic standards. The water vapour exists at temperatures of around minus 63 degrees Celsius, which sounds freezing, but in space that's relatively warm, especially for such distant regions. There's also pressure to consider, though it's not the kind you'd feel underwater. It's more about density, how concentrated the gas is compared to the emptiness of space around it. In this case, the water exists in a region that is denser and more energetic than the average interstellar medium, creating conditions where molecules can form and persist despite the surrounding chaos. It's a delicate balance in a way. On one side, you have intense radiation that could break molecules apart. On the other, you have enough density and shielding for water to exist, drifting in enormous clouds. So what we end up with is something that doesn't quite fit into our usual categories. Not a sea, not a cloud in the everyday sense, but something in between. A cosmic reservoir shaped by forces far beyond anything we experience here. And the more scientists studied it, the more it raised new questions. For example, how did so much water form so early in the universe? Because APM 08279 plus 5255 is incredibly distant. Its light has taken billions of years to reach us. That means we're not seeing it as it is now, but as it was long ago, when the universe itself was much younger. And yet, even at that early stage, there was already enough oxygen and hydrogen, the basic ingredients of water, combining in large quantities. This suggests that the processes that create these elements, inside stars through nuclear fusion, must have been happening relatively quickly in cosmic terms. Stars formed, lived, and died, spreading heavier elements into space, where they could eventually combine into molecules like water. So in a sense, this distant ocean is not just a curiosity, it's a clue, a sign that the building blocks of something familiar, something we associate with life and habitability, were already present in the universe much earlier than we might have expected. But of course, this doesn't mean there's life there. The conditions are far too extreme for anything we know. The radiation alone would make it an incredibly hostile environment, and without solid surfaces, stable temperatures, or the right chemistry, it's not a place where oceans behave like they do here. Still, it's hard not to feel a certain connection. Water is such a central part of our existence. It shapes our planet, our bodies, our daily lives. And to find it, not just anywhere, but in such vast amounts, so far away, creates a quiet sense of continuity, as if the same simple molecule is threading its way through the universe, appearing in places both familiar and completely alien. And maybe that's part of what makes this discovery so compelling. It takes something we know so well and stretches it beyond recognition, turning it into something almost abstract, yet still, in a fundamental way, the same. So as we continue exploring this idea, it helps to gently shift perspective. Instead of imagining waves or coastlines, try thinking of this ocean as a presence, a vast invisible structure woven into the fabric of a distant galaxy, quietly existing while light from it travels across billions of years to reach us, And as we move forward, there's a natural question that begins to form. If this much water exists out there, surrounding something as powerful as a quasar, what exactly is it like to be near such an object? What would you actually experience, not just in terms of distance or scale, but in the way space itself behaves in that environment? Somewhere in the late 20th century, long before anyone imagined talking about oceans in deep space, astronomers were quietly cataloguing points of light. Not stars in the usual sense, not the kind you might pick out in the night sky, but much more distant objects. Faint, flickering signals that had travelled for billions of years before reaching Earth, arriving as tiny whispers of energy in large, sensitive telescopes. At first glance, many of these objects didn't look particularly special. They appeared as small, bright spots, almost like stars, but something about them didn't quite fit. Their light was unusual, their brightness didn't behave the way nearby stars did. And most importantly, when scientists began to analyse that light more carefully, it told a very different story. One of those objects would later be named APM 08279 +5255. But at the beginning, it was simply a curiosity, a point of light in the distant universe that refused to behave like anything familiar. Now, if you imagine astronomers at work, it's often less dramatic than people expect. There's no sudden flash of realization, no dramatic music playing in the background. Instead, it's a slow process. Observations, measurements, comparisons, looking at patterns, checking data, sometimes going back over the same information again and again just to be sure nothing was missed. And in this case, what caught their attention wasn't just how bright this object was, but how unusually bright it seemed compared to its distance. Because distance in astronomy is everything. Light fades as it travels. The farther something is, the dimmer it should appear. That's a simple, reliable rule. So when something incredibly far away still appears extremely bright, it usually means one of two things. Either it's much closer than we thought, or it's unbelievably powerful. In the case of APM 08279 +5255, it turned out to be the second. When astronomers measured its redshift, the stretching of light caused by the expansion of the universe, they realized they were looking at something that existed billions of years ago. The light reaching Earth today had begun its journey when the universe was much younger than it is now, and yet, despite that enormous distance, it was shining with an intensity that suggested something extraordinary was happening at its core. That's when it began to fall into a category known as quasars. Now, quasars are among the most luminous objects in the universe. They are powered by supermassive black holes, surrounded by vast disks of gas and dust that spiral inward, heating up and releasing enormous amounts of energy in the process. But even among quasars, this one stood out. It wasn't just bright, it was exceptionally bright. So bright, in fact, that astronomers began to suspect that something else might be going on. Because sometimes in the universe, things aren't just what they seem at first glance. There's a phenomenon known as gravitational lensing, where the gravity of a massive object like a galaxy bends and magnifies the light from something behind it. It acts almost like a cosmic magnifying glass, making distant objects appear brighter and sometimes even distorting their shape. And as it turns out, APM 08279 +5255 is affected by this exact effect. Between us and this distant quasar, there is a massive structure, likely a galaxy, whose gravity bends the light travelling toward Earth. This magnification makes the quasar appear even brighter than it already is. So, what astronomers were seeing wasn't just a powerful object, but a powerful object being amplified by the universe itself. And yet, even after accounting for this lensing effect, the quasar remained incredibly luminous, which meant one thing. Whatever was happening there, it was happening on a scale that pushed the limits of what scientists understood at the time. Naturally, this led to more detailed observations. Different telescopes were pointed toward it. Not just optical ones, but instruments that could detect radio waves, infrared signals, and other parts of the electromagnetic spectrum. Because light, in all its forms, carries information, and if you listen carefully enough, it starts to tell a story. At first, the story was about energy. The quasar was emitting vast amounts of it, radiation pouring out from the region around its central black hole, driven by matter falling inward at incredible speeds. The kind of environment where temperatures soar, where particles collide, where space itself feels active rather than empty. But then, as observations became more precise, something unexpected began to emerge. A pattern in the data that didn't quite match the usual signatures of hot gas or energetic particles alone. It was subtle, easy to overlook at first, but once noticed, it was difficult to ignore. Astronomers studying the light coming from this region began to detect specific absorption and emission lines, small dips and peaks in the spectrum that correspond to particular molecules, and among those signatures was something familiar, something almost comforting in its simplicity: water. Now, at this stage, it wasn't immediately obvious what that meant. After all, water has been detected in space before. It exists in molecular clouds, in star-forming regions, even in the atmospheres of certain planets and moons. So the presence of water itself wasn't shocking. But the amount, that's where things started to become truly unusual. As scientists refined their measurements, using powerful radio telescopes capable of detecting faint signals from across the universe, they began to estimate just how much water vapor was present around APM 08279 plus 5255, and the numbers that came back were difficult to process, not because they were uncertain, but because they were so large that they stretched the imagination. We're used to thinking in terms of litres, maybe cubic kilometres when it comes to oceans. Even the largest bodies of water on Earth can be measured, mapped, and understood within a certain scale. But this was different. This was a region spanning hundreds of light years, filled with water vapour. To give that some context, a single light year is about 9.5 trillion kilometres. So when you start talking about structures hundreds of light years across, the distances involved are already immense, and within that vast space there was enough water to make Earth's oceans seem almost negligible by comparison. At this point, the discovery shifted from being simply interesting to something much more profound, because it raised questions that went beyond the object itself. How could so much water exist in such an extreme environment? Where did it come from? And perhaps most intriguingly, what does this tell us about the universe as a whole? To answer those questions, scientists had to step back and think about the bigger picture. Water, at its most basic level, is made of hydrogen and oxygen. Hydrogen is the most abundant element in the universe. It formed shortly after the Big Bang and exists almost everywhere. Oxygen, on the other hand, is created inside stars through nuclear fusion and then released into space when those stars die, often in dramatic explosions known as supernovae. So, for water to exist in large quantities, you need both of these ingredients to come together under the right conditions, and that means stars must have already formed, lived their lives, and enriched the surrounding space with heavier elements. The fact that this was happening so early in the universe's history, as indicated by the distance of APM 08279 plus 5255, suggested that these processes were occurring faster than some models had predicted. In other words, the universe was building complexity sooner than expected. It wasn't just a simple, uniform expanse of hydrogen and helium for long. It was already evolving, already forming structures, already creating the chemical ingredients that would later become important for things like planets, atmospheres, and perhaps even life elsewhere. But while those broader implications were fascinating, there was still something quietly astonishing about the discovery itself. Because even if you understand the chemistry, even if you follow the logic of star formation and molecular clouds, the sheer scale of it remains hard to grasp. An ocean, not on a planet, not contained by gravity in the way we're used to, but spread across space, influenced by a supermassive black hole. existing as a vast drifting reservoir of molecules. It's the kind of idea that feels almost contradictory at first. Water, something so familiar placed in a setting so extreme. And yet that contrast is exactly what makes it so compelling, because it reminds us that the universe doesn't organize itself according to our expectations. Things we associate with calm, like water, can exist alongside things we associate with chaos, like quasars. And somehow, both can be part of the same system. As researchers continue to study APM 08279 plus 5255, they began to piece together a more detailed picture of its environment. The water vapour wasn't just sitting there quietly. It was part of a dynamic system, influenced by radiation, by gravity, by the movement of gas and dust. The region around the quasar was dense compared to typical interstellar space, providing the conditions needed for molecules to form and survive. At the same time, it was being heated and energized by the intense activity near the black hole. This created a kind of balance, not stable in the way a calm lake is stable, but stable enough for water to persist over long periods of time. And as more observations came in using increasingly advanced instruments, the initial discovery was confirmed and refined. It wasn't a mistake. It wasn't a misinterpretation. It was real. A vast amount of water, existing billions of light years away, surrounding one of the brightest objects in the universe. And once that realization settled in, it naturally led to the next question. If this is what we're seeing from so far away, just from analysing light that has travelled across the universe, what exactly is this object at its core? At this point, it helps to slow things down just a little and take a closer look at the object at the centre of all this. Because while the idea of a vast ocean in space is certainly intriguing, it doesn't exist on its own. It's shaped, heated and sustained by something much more powerful, something that, at first glance, doesn't seem like it should have anything to do with water at all. So what exactly is APM 08279 plus 5255? If you were to point a telescope at it, you wouldn't see anything resembling an ocean or even a recognizable structure. You'd see a bright, distant point of light, something that looks almost star-like, steady and intense, quietly shining from far beyond our galaxy. But that simple appearance is a bit misleading, because what you're actually looking at is not a single object, but a complex system, one that stretches across enormous distances and is powered by forces that are difficult to fully picture. To begin with, APM 08279 plus 5255 is what astronomers call a quasar. Now, we've mentioned that word already, but it's worth unpacking it slowly, because understanding quasars is the key to understanding everything else that follows. The word itself comes from quasi-stellar object, which basically means something that looks like a star but isn't. And that's exactly how quasars were first discovered. In the early days of radio astronomy, scientists detected strong radio signals coming from certain points in the sky. When they tried to match those signals with visible objects, they found tiny star-like sources. But when they studied the light from those sources more carefully, they realized they were incredibly far away. Far too far away to be ordinary stars, and yet, despite that distance, they were shining with extraordinary brightness. That combination, small appearance, enormous distance, and extreme luminosity, led to a simple but surprising conclusion. These were not stars at all. They were the bright centres of distant galaxies, powered by something far more energetic. At the heart of every quasar lies a supermassive black hole. Not the kind formed from a collapsing star, but something much larger. Millions or even billions of times the mass of our Sun, sitting at the centre of a galaxy, quietly shaping everything around it. Now, when people hear black hole, they often think of something that simply pulls things in and never lets them escape. A kind of cosmic vacuum cleaner. And while there's some truth to that, it's only part of the story. Because the most interesting activity doesn't happen inside the black hole itself, but just outside it. Surrounding the black hole is what's known as an accretion disk, a vast rotating disk of gas, dust and other material that is gradually spiraling inward. As this material falls closer to the black hole, it doesn't just drop straight in. It speeds up, heats up and begins to glow, and not just a little. The friction and compression in the accretion disk can raise temperatures to millions of degrees, causing the material to emit enormous amounts of energy across the electromagnetic spectrum. Visible light, X-rays, ultraviolet radiation, all pouring out from a region that, in cosmic terms, is relatively small. This is what makes quasars so bright. It's not the black hole itself that shines, but the matter around it, heated to extreme temperatures as it falls inward. And in the case of APM 08279 + 5255, this process is happening on a particularly large and energetic scale. The black hole at its centre is estimated to be tens of billions of times more massive than our Sun. To put that into perspective, the black hole at the centre of our own galaxy, the Milky Way, is about 4 million times the mass of the Sun, which already sounds enormous. But compared to APM 08279 + 5255, it's relatively modest. So you can imagine the difference in scale. A much larger black hole means a stronger gravitational pull, which means more material being drawn in, which means more energy being released. And all of that contributes to the incredible brightness that first caught astronomers' attention. But there's another layer to this story as well. Because as we mentioned earlier, APM 08279 + 5255 isn't just bright on its own. Its light is also being magnified by gravitational lensing. Between us and the quasar, there is a massive object, likely a galaxy, whose gravity bends the light travelling toward Earth. This bending doesn't just change the direction of the light, it can also amplify it, making distant objects appear brighter than they actually are. In some cases, gravitational lensing can even create multiple images of the same object, like reflections in a cosmic mirror. With APM 08279 + 5255, this effect enhances its already impressive luminosity, allowing us to study it in greater detail than we otherwise could. It's almost as if the universe is giving us a little help, acting as a natural telescope. Now, even with that assistance, observing something this distant is no small task. The light we receive from APM 08279 + 5255 has been travelling for billions of years. That means we're not seeing it as it is today, but as it was in the distant past when the universe was much younger. In a sense, every observation is also a look back in time, and what we see in that ancient light tells us something important. It tells us that even early in the universe's history, there were already massive black holes, already forming quasars, already creating environments where complex molecules like water could exist. That's a lot happening, relatively quickly, on cosmic timescales. But let's come back to the quasar itself, because there's one more detail that helps complete the picture. In addition to the accretion disk, many quasars also produce powerful jets. These are narrow streams of charged particles that are launched from the regions near the black hole at speeds close to that of light. They can extend for thousands, even millions of light years, carrying energy far out into the surrounding galaxy. Now, not all quasars have jets that are easily visible from Earth, and in the case of APM 08279 + 5255, the details of its jets are still being studied. But the possibility of such structures adds another layer of complexity to the environment. So, when you step back and look at the whole system, it starts to come together. At the centre, a supermassive black hole. Around it, a blazing accretion disk, releasing enormous amounts of energy. Further out, vast clouds of gas and dust influenced by radiation and gravity. And within those clouds, among other molecules, water vapour spread across an enormous region. It's not a quiet place. It's not still. Everything is in motion. Gas is flowing inward, radiation is pushing outward, energy is being transferred in multiple ways at once. And yet, within that activity, certain structures can persist. certain molecules can form and survive, including water. Which brings us back to that idea of a cosmic ocean, because while the quasar provides the energy and the gravitational framework, the water itself exists in the surrounding regions, shaped by these forces but not entirely overwhelmed by them. It's almost like a delicate balance. Too much radiation, and the molecules would break apart. Too little density, and they wouldn't form in the first place. But in this particular environment, the conditions line up just enough to allow for something remarkable. A reservoir of water, vast beyond easy comparison, existing in one of the most energetic regions of the universe. Now that we have a clearer sense of what APM 08279 plus 5255 is, a quasar powered by a supermassive black hole, the question becomes a little more focused. What is it about quasars in general that makes them so bright, so powerful, and so important in our understanding of the universe? If you take a moment and imagine looking up at the night sky, what you usually see feels calm. A scattering of stars, maybe a faint band of the Milky Way, perhaps a planet shining a little brighter than the rest. Everything appears steady, distant, almost quiet. It's easy to think of the universe as something slow and gentle, unfolding at a pace far removed from anything intense. But that impression, as comforting as it is, only tells a very small part of the story. Because hidden among those distant points of light are objects so bright, so energetic, that they outshine entire galaxies. Not by a small margin, but by factors that stretch into the hundreds or even thousands. And among these objects, quasars stand as some of the most extreme examples, including of course APM 08279 plus 5255. Now, calling quasars bright doesn't quite capture what's really happening. Brightness, in everyday terms, is something we experience with a light bulb or the sun reflecting off a surface. But in astronomy, brightness often means something deeper. It's not just about how something looks from a distance, but how much energy it's actually producing. And quasars produce an extraordinary amount. To get a gentle sense of scale, imagine taking all the stars in a large galaxy, hundreds of billions of them, each burning steadily through nuclear fusion, each releasing light and heat into space. Now imagine adding up all of that energy. That's what a galaxy shines with, and yet a single quasar can rival or even exceed that total. Not because it contains more stars, but because of what's happening at its centre. At the heart of every quasar lies a supermassive black hole, surrounded by an accretion disk, a rotating structure of gas and dust that gradually spirals inward. As this material moves closer to the black hole, it speeds up and compresses, generating enormous heat. That heat turns into radiation, and that radiation is what we see. But here's where it becomes particularly interesting. The efficiency of this process, converting matter into energy, is surprisingly high. In ordinary stars like our Sun, nuclear fusion converts only a small fraction of mass into energy. Most of the material remains, slowly fusing over millions or billions of years. In an accretion disk, however, the conversion can be much more dramatic. As matter falls inward, a significant portion of its mass is transformed into energy before it ever crosses the event horizon. The result is an output that far exceeds what you'd expect from the same amount of material in a star. So in a way, quasars are not just bright because they are large, but because they are efficient. They make the most of what they consume. And in systems like APM 08279 plus 5255, there is plenty to consume. Gas from the surrounding galaxy flows inward, feeding the black hole over long periods of time. This steady supply allows the quasar to remain active, continuing to shine across vast distances. But brightness alone isn't what makes quasars so useful to astronomers. It's also the fact that they can be seen from incredibly far away. Because they are so luminous, quasars act like beacons in the universe. Even when they are billions of light years away, their light can still be detected. That means when we observe them, we are looking deep into the past. Light from APM 08279 plus 5255, for example, has travelled for billions of years before reaching Earth. So what we're seeing is not the quasar as it is now, but as it was when the universe was much younger. This makes quasars valuable tools for studying cosmic history. They help us understand how galaxies formed, how black holes grew, and how matter was distributed in the early universe. And sometimes, as in this case, they reveal something unexpected. Because the light from a quasar doesn't just tell us about the quasar itself, it also carries information about everything it has passed through along the way. As light travels across space, it interacts with gas and dust. Certain wavelengths are absorbed, others are emitted, leaving behind a kind of record. By analysing these patterns, astronomers can identify the presence of different elements and molecules, even at enormous distances. That's how the water around APM 08279 plus 5255 was discovered. Not by seeing it directly, but by reading the subtle signals embedded in the quasar's light. So in that sense, the brightness of the quasar becomes more than just a feature. It becomes a tool, a way of illuminating regions of space that would otherwise remain invisible. Now there's another aspect of quasars that adds to their role as cosmic beacons. They don't just shine steadily. They can vary. The light from a quasar can fluctuate over time, sometimes over days, sometimes over longer periods. These changes are often linked to the dynamics of the accretion disk, how material is flowing, how it's heating up, how it's interacting with magnetic fields. And while these variations might seem like small details, they can tell astronomers a great deal. For example, by observing how quickly a quasar's brightness changes, scientists can estimate the size of the region producing that light. Faster changes usually mean smaller regions, because larger structures tend to evolve more slowly. This kind of reasoning helps build a picture of what's happening near the black hole, even though we can't see it directly. It's a bit like listening to distant thunder and trying to understand the shape of the storm. You don't see everything, but the signals give you clues. In the case of APM 08279 plus 5255, those clues point to a system that is not only powerful, but also complex. There are layers to it. The central black hole, the accretion disk, the surrounding gas, the effects of radiation, the influence of gravity from intervening objects, all interacting in ways that shape what we observe. And within that complexity, the presence of water adds an extra dimension, because it shows that even in environments dominated by extreme energy, there can still be pockets where molecules form and persist. Which brings us back gently to the idea of scale, because it's one thing to say that quasars are bright, or that they act as beacons, or even that they can reveal distant water. But it's another thing entirely to grasp just how large the structures around them can be. The region containing water around APM 08279 plus 5255 isn't a small cloud or a thin layer. It extends across hundreds of light years, making it one of the largest known reservoirs of water in the universe. If quasars are capable of illuminating such vast regions, and if the environments around them can support structures on this scale, how do we begin to measure something like that? How do we compare it to anything familiar? If you gently follow the trail of everything we've explored so far, the brightness, the immense energy, the vast clouds of gas, and even that enormous reservoir of water, it all leads back to one central presence. Not something you can see directly, not something that shines, but something that shapes everything around it. At the heart of APM 08279 plus 5255 lies a supermassive black hole. And despite the dramatic name, it's not quite the kind of object that pulls everything in like a cosmic vacuum cleaner, endlessly swallowing whatever comes too close. That's a common image, but it's a bit misleading. In reality, a black hole is more like a region of space where gravity has become so strong that beyond a certain boundary, nothing can escape. Not light, not matter, not even information as far as we currently understand it. That boundary is called the event horizon. But interestingly, everything we've been talking about, the brightness, the radiation, the movement of gas, all of it happens outside that boundary. The black hole itself is completely dark, so if it doesn't emit light, if it doesn't glow or flicker, then how does it end up powering one of the brightest objects in the universe? The answer lies in what surrounds it. Imagine for a moment a vast region of space filled with gas and dust, material left over from earlier stages of the galaxy's life. Slowly, under the influence of gravity, some of that material begins to drift inward. At first, the motion is gentle, but as it gets closer, something begins to change. The material doesn't fall straight in. Instead, it starts to spiral. This happens because of angular momentum, the same reason planets orbit stars instead of crashing directly into them. As the gas moves inward, it forms a rotating disk around the black hole, what astronomers call an accretion disk. And this is where things begin to heat up, quite literally. As particles in the disk move closer together, they collide. They rub against each other. They compress under immense pressure. And all of that motion and friction generates heat. A lot of heat. Temperatures in the inner regions of the disk can reach millions of degrees, hot enough that the material begins to glow intensely, emitting radiation across a wide range of wavelengths. This glowing disk is what we actually see when we observe a quasar, not the black hole itself, but the chaos happening just outside it. And in the case of APM 08279 plus 5255, this process is happening on an enormous scale. The black hole at its centre is estimated to be tens of billions of times the mass of our Sun. Now, it's worth pausing on that number for a moment, because it's easy to say it quickly and move on, but it represents something almost beyond everyday understanding. Our Sun contains about 99.8% of the mass in our entire solar system. It dominates everything around it, from the planets to the smallest grains of dust. Now imagine something billions of times more massive than that. Not just larger, but so massive that its gravitational influence extends across vast regions of space, shaping the motion of gas, stars, and everything else nearby. That's the kind of object sitting at the centre of this system, and because it's so massive, it has an equally enormous appetite. Material from the surrounding galaxy is constantly being drawn toward it. Not all at once, not in a sudden collapse, but gradually, over time, forming that swirling disk we talked about. And as long as there is material to feed on, the system remains active, the disk continues to glow, the quasar continues to shine. But there's another layer to this that makes things even more interesting, because not all of the material that approaches the black hole actually falls in. Some of it gets caught up in powerful outflows. Radiation from the accretion disk can push gas outward, creating winds that move at incredibly high speeds. In some cases, magnetic fields can channel material into narrow jets that shoot out from the poles of the black hole. These jets can travel for thousands, even millions of light years, carrying energy far beyond the immediate surroundings. So what you end up with is not just a simple system where everything moves inward. It's more like a balance between inward and outward motion. Gas falling in, energy pushing out, radiation interacting with matter, all happening at the same time. And within that dynamic environment, certain regions can become dense enough and shielded enough for molecules to form, including water. Which brings us back quietly to that idea of a cosmic ocean. Because while the black hole itself doesn't contain the water, it plays a crucial role in shaping the conditions where that water exists. Its gravity pulls material inward, increasing density. Its energy output heats and excites the surrounding gas. And the interplay between these forces creates pockets where molecules can form and survive. It's a bit like having a furnace at the centre of a system, one that is both destructive and creative at the same time. Too close, and everything is torn apart, heated beyond recognition. But farther out, at just the right distance, the environment becomes complex rather than chaotic, structured rather than completely random. And that's where the water lives, not in a calm, stable ocean like we know on Earth, but in vast, drifting clouds, influenced by everything happening at the centre. Now there's one more aspect of black holes that's worth touching on here, because it connects in an interesting way to how we think about space and time. Near a black hole, gravity becomes extremely strong, and according to Einstein's theory of general relativity, strong gravity doesn't just affect motion, it affects time itself. Clocks closer to a massive object tick more slowly compared to those farther away. This effect is known as gravitational time dilation. In everyday life, the difference is far too small to notice, but near a supermassive black hole, especially one as large as the one in APM 08279 plus 5255, the effect becomes more significant. If you could somehow observe this region from a safe distance, you might notice that processes near the black hole appear to unfold more slowly compared to regions farther out. Now, of course, this is more of a thought experiment than a practical observation. The environment near a quasar is far too extreme for anything like a human observer to exist. But it's still a useful way to think about how different this region is from anything we experience. Space behaves differently, time behaves differently. And yet, within all of that, familiar molecules like water can still exist, which is a quiet reminder that the universe often combines the familiar and the unfamiliar in ways that feel surprising at first. So, when we think about the ocean around APM 08279 plus 5255, it's not just a collection of molecules floating in space, it's part of a much larger system. A system powered by one of the most massive black holes we know, shaped by gravity, energy and motion on scales that stretch far beyond anything we encounter in everyday life. By now, the picture has grown a little wider. There's a supermassive black hole at the centre, surrounded by a blazing disk of matter, all of it wrapped in a vast, complex environment where even something as familiar as water can exist on an unimaginable scale. But there's another layer to this story that quietly sits underneath everything we've talked about so far, and it has to do with distance. Because when we say that APM 08279 plus 5255 is far away, we're not just talking about something that would take a long time to reach. We're talking about something so distant that even light, the fastest thing we know, has taken billions of years to get here. Now, it's easy to say that quickly and move on, but it's worth slowing down and letting that idea settle in a bit. Light travels at about 300,000 kilometers per second. That's fast enough to circle the Earth more than 7 times in a single second. If you turned on a flashlight and pointed it into space, that beam would be moving outward at that speed, crossing vast distances almost instantly, at least from our everyday perspective. But even at that speed, space is so large that it takes time, a lot of time. When astronomers measure the distance to APM 08279 plus 5255, they find that its light has been travelling for more than 12 billion years before reaching Earth, which means something rather unusual. We're not seeing it as it is now, we're seeing it as it was, at a time when the universe itself was much younger. In fact, when that light began its journey, our solar system didn't exist. The Earth hadn't formed. There were no oceans here, no continents, no life. Just a very different universe, still in the earlier stages of its long history. And yet, that ancient light has been moving steadily ever since, crossing enormous stretches of space, passing by galaxies, drifting through regions of gas and dust, all the while carrying information about its origin. Until, eventually, a tiny fraction of it arrives here, at our planet, at our telescopes, at our instruments, and somehow we're able to read it. There's something quietly remarkable about that, because it means that when astronomers study APM 08279 plus 5255, they're not just observing a distant object, they're looking back in time. Each photon of light is like a messenger from the past, carrying details about what was happening billions of years ago. And by analysing that light, its colour, its intensity, the way it has been stretched and shifted, scientists can reconstruct a picture of that distant environment. Now, one of the key ideas that helps with this is something called redshift. As the universe expands, space itself stretches. and as space stretches, the light travelling through it is stretched as well. Wavelengths become longer, shifting toward the red end of the spectrum. The greater the redshift, the farther away the object is, and the further back in time we're seeing it. In the case of APM 08279 plus 5255, the redshift is significant, which tells us two things at once. First, that it is incredibly distant, and second, that the light we're seeing left it, when the universe was only a fraction of its current age. So in a way, this quasar becomes a kind of time capsule, a glimpse into an earlier era, and what makes it even more interesting is what we find inside that glimpse. Because despite being so early in cosmic history, we're already seeing complex structures, a massive black hole, a bright accretion disk, and surrounding it, enormous clouds of gas, including water vapour. That last part is especially intriguing, because it suggests that the processes needed to create water, the formation of stars, the production of heavier elements like oxygen, and the combination of those elements into molecules had already taken place by that time. In other words, the universe wasn't just young, it was already active, already building complexity, already forming the ingredients that in other places and times would eventually become part of planets, atmospheres, and maybe even living systems. But let's return, gently, to the journey of light itself, because there's another aspect of it that adds a subtle layer to everything we've been discussing. Light doesn't always travel in a straight, uninterrupted path. As it moves through the universe, it can be influenced by gravity. Large objects like galaxies or clusters of galaxies can bend the path of light, a phenomenon known as gravitational lensing. We mentioned this earlier, but here it becomes particularly relevant, because the light from APM 08279 plus 5255 doesn't reach us directly. On its way, it passes near massive structures whose gravity bends and magnifies it. This bending can stretch the image, sometimes even splitting it into multiple components, though in this case the effect is more about amplification than duplication. The result is that the quasar appears brighter than it would otherwise, and that brightness makes it easier for us to study. It's as if the universe has placed a natural lens along the path, helping us see something that might have been too faint to detect otherwise. But this also means that what we observe is not just a simple, direct view, it's a view shaped by the journey itself, by everything the light has encountered along the way. So when we look at APM 08279 plus 5255, we're seeing a combination of its original emission and the effects of cosmic structures between us and it. It's a layered observation, and yet despite all of that complexity, the information remains surprisingly clear. Clear enough to identify molecules, clear enough to estimate distances and temperatures, clear enough to tell us that somewhere, billions of years ago, there existed a vast reservoir of water in a region shaped by one of the most powerful objects in the universe. Now there's something else that often gets overlooked when thinking about these immense distances, and that is how quiet the journey of light really is. We tend to imagine space as busy or crowded, but in reality it's mostly empty. So when light leaves a distant quasar, it doesn't travel through a thick medium. It moves through vast stretches of near vacuum, uninterrupted for long periods. No sound, no resistance, just motion. A steady, silent progression across billions of years. And that continuity is what allows us to observe the universe the way we do. It's what connects us to distant objects. It's what makes astronomy possible, because without that uninterrupted journey, the information would never reach us. So, in a sense, every observation we make is the result of an incredibly long chain of events. Light emitted long ago, travelling across space, passing through gravitational fields, being collected by telescopes, analysed by instruments, interpreted by scientists. All of it coming together to form a picture. And that picture, in this case, includes something as unexpected as a cosmic ocean, which brings us to a gentle realization. The water around APM 08279 plus 5255 is not something we can touch, or see directly, or experience in the way we experience water here on Earth. It exists at a distance so great that it feels almost abstract. And yet, through the journey of light, it becomes something we can study, something we can understand, at least in part, something we can include in our picture of the universe. And perhaps that's part of what makes this discovery so quietly fascinating. It's not just about the object itself, or even the water it contains. It's about the connection. The idea that something so far away, so distant in both space and time can still reach us, can still be known, can still become part of our understanding. At some point, after all the measurements, the calculations, and the careful observation of light that had travelled longer than anything we experience in daily life, something very specific began to stand out. Not brightness, not distance, but a pattern, a small, subtle feature hidden inside the light coming from APM 08279 + 5255. Now, the interesting thing about astronomy is that discoveries don't usually arrive all at once. They tend to unfold slowly, almost quietly, as more data is gathered, and small details begin to align in ways that weren't obvious at first. And in this case, the key detail came from studying the spectrum of light. When astronomers observe something far away, they don't just look at how bright it is. They break its light apart into its component wavelengths, spreading it out like a very detailed rainbow. And within that rainbow, there are tiny patterns, lines, gaps, signals that correspond to specific atoms and molecules. Each one acts like a fingerprint. Hydrogen leaves one kind of mark, carbon leaves another, and water, even in its vapor form, has its own distinct signature. So, as scientists examined the light from this distant quasar, they began to notice something familiar appearing again and again in the data. A pattern that matched water vapor. At first, it wasn't something to rush toward, because detecting molecules at such distances is delicate work. There's always the possibility of interference, of signals overlapping, of something closer to Earth creating a similar pattern. So the first step is always caution. Check the data, check it again, compare it with models, look for consistency. And slowly, as more observations came in, the signal held steady. It wasn't noise, it wasn't an artifact, it was real, water, and not just a trace amount, not just a faint hint, but something much larger. Now, this is where the discovery begins to shift from interesting to quietly astonishing. Because once scientists confirmed the presence of water vapor, the next question was naturally about quantity. How much water are we actually talking about? And answering that question required a different kind of thinking. You can't scoop up water from a region billions of light years away. You can't measure it directly. Instead, you infer it from the strength of the signal, from how much light is being absorbed and emitted at specific wavelengths. Stronger signals generally indicate more molecules, and as the calculations were refined, the estimates began to grow, and grow, and grow, until they reached a point where the numbers no longer felt intuitive. The region surrounding APM 08279 + 5255 was found to contain enough water vapor to exceed the total amount of water in Earth's oceans by more than 140 trillion times. It's one of those numbers that doesn't quite settle easily in the mind, because we're used to thinking about water in terms of lakes, rivers, oceans. Even the largest ocean on Earth, the Pacific, has a scale that, while vast, can still be mapped, measured, and understood. But here, the scale stretches far beyond anything like that. We're no longer talking about surfaces or shorelines. We're talking about volume spread across hundreds of light years, a kind of presence rather than a place. And when that realization began to settle in, it changed the way scientists thought about the discovery. Because this wasn't just a detection of water, it was the identification of one of the largest known reservoirs of water in the entire universe. Now, it's worth pausing for a moment and considering how unexpected that really is. The environment around a quasar is intense, radiation levels are high, energy is constantly being released, particles are moving at incredible speeds. It doesn't immediately feel like a place where delicate molecules would persist. And yet, here they were, not only present, but abundant. So naturally this raised another question. How is that possible? Why isn't the water simply destroyed by the surrounding conditions? The answer lies in the structure of the region itself. While the inner areas near the black hole are indeed extreme, farther out there are zones where the conditions become more balanced. Still energetic, still dynamic, but not overwhelmingly destructive. In these regions, gas can cool just enough, densities can increase just enough, and radiation can be absorbed or scattered in ways that allow molecules to form and survive. Water, in particular, forms when hydrogen and oxygen combine under the right conditions. Hydrogen is everywhere. Oxygen, as we mentioned earlier, comes from stars. So once those elements are present and once the environment allows for it, water can begin to appear, and over time, as more material accumulates, as more reactions occur, the amount can grow. In the case of APM 08279 plus 5255, it seems that these processes have been happening on a very large scale. Which brings us back to that moment of discovery. Because it wasn't just about seeing a new signal, it was about realizing what that signal meant. That in one of the most energetic regions of the universe, there existed something we associate with calm, with familiarity, with life on Earth. Even if, in this context, it behaves very differently, there's something quietly striking about that contrast. A supermassive black hole surrounded by intense radiation, and within that environment, water. It doesn't smooth things out or make them gentle, but it adds a layer of complexity, a reminder that the universe often brings together elements that don't seem like they belong side by side, and yet they do. Now, another interesting detail about this discovery is how it connects to the broader study of the universe. Because detecting water at such distances doesn't just tell us about one object, it tells us something about the conditions in the early universe. It suggests that the ingredients for water were already widespread, that chemical complexity was already developing, that even billions of years ago the processes that create molecules were active, and that opens the door to further questions. If water exists there, in such abundance, where else might it exist? In smaller amounts, in different environments, in places that are less extreme. And how common is it really when we look at the universe as a whole? These are the kinds of questions that naturally follow from a discovery like this. Not urgent, not pressing, but quietly expanding the picture, adding new possibilities. Now, there's also something worth noticing about the way this discovery fits into the broader flow of scientific understanding. It didn't arrive as a single dramatic moment. There wasn't one observation that suddenly revealed everything. Instead, it was built up over time. Different teams, different instruments, different observations, all contributing pieces to the same puzzle. And eventually those pieces came together. A signal confirmed, a quantity estimated, a conclusion drawn. And with that, the idea of the largest ocean in the universe began to take shape. Not as something seen directly, but as something inferred, carefully, from the light that reached us. Which in a way makes it even more remarkable, because it shows how much we can learn without ever going there, without ever touching or seeing the object in the usual sense, just by reading the signals that arrive from far away. Now that we know how the water was found and how much of it there is, the next question becomes a little more grounded. What does that scale actually look like when we try to compare it to something familiar? At first, hearing that water exists around APM 08279 plus 5255 might sound like an interesting detail, something you could almost file away alongside other discoveries. Water on Mars, water on icy moons, water in distant clouds. But the moment you begin to look a little closer, the scale quietly shifts. Because this isn't just water, and it isn't just a cloud. It's something that pushes the limits of what that word usually means. An ocean. Not in the familiar sense of waves and shorelines, but in sheer quantity, in volume, in presence. And to really get a sense of it, it helps to slow down and gently build the picture step by step. Let's begin somewhere comfortable. Think of Earth's oceans. All of them together, the Pacific, the Atlantic, the Indian, the Southern, the Arctic, they contain about 1.4 billion cubic kilometres of water. That's already a number large enough that most of us don't try to picture it directly. Instead, we think in terms of images, endless horizons, deep blue expanses, the quiet movement of tides. Now imagine taking all of that water, every drop, and multiplying it. Not twice, not 100 times, but trillions of times over. That's the kind of scale we're dealing with here. The water surrounding APM 08279 plus 5255 is estimated to be at least 140 trillion times the amount found in all of Earth's oceans combined. And even that number, as large as it is, doesn't quite tell the full story, because the water isn't gathered into a single place. It's spread out across a region that spans hundreds of light years. Now it's worth pausing again for just a moment, because hundreds of light years can easily slip past without fully registering. A single light year is the distance light travels in 1 year, about 9.5 trillion kilometres. So when we say hundreds of light years, we're talking about distances so vast that even the journey of light becomes something that takes centuries to cross from one side to the other, and within that immense region there exists this reservoir of water vapour. Not flowing, not pooling, but present, drifting, interacting, shaped by the environment around it. Which brings us to something important. This ocean is not liquid. There are no waves, no currents, no surface tension pulling droplets together. Instead, the water exists as vapour mixed with other gases, forming enormous clouds. And yet, despite that difference, the word ocean still feels appropriate. Because what defines an ocean, at least in this context, is not its state, but its scale, its abundance, its overwhelming presence compared to anything else we know. And when you begin to think of it that way, the idea becomes a little clearer. It's an ocean in the same sense that a desert is vast, even if its grains of sand are separate. Or a forest is immense, even though it's made of individual trees. Here, the ocean is a vast collection of water molecules spread across space, forming a structure that is almost impossible to fully take in at once. Now, there's another layer to this that adds to the sense of scale. Because the density of this water vapour, while higher than typical interstellar space, is still incredibly low compared to anything we experience on Earth. If you could somehow move through it, which is more of a thought experiment than a practical possibility, you wouldn't feel like you were moving through water. You wouldn't even feel resistance. It would feel more like a very thin gas, almost empty. And yet, because the region is so large, the total amount adds up to something enormous. It's a bit like imagining a very light fog that stretches not for meters or kilometers, but for hundreds of light years. Individually, each part feels sparse, but collectively it becomes vast. Now, let's gently connect that back to the environment we've been building. This ocean doesn't exist in isolation. It surrounds a quasar powered by a supermassive black hole, which means that everything about it is influenced by energy. Radiation from the accretion disk heats the surrounding gas. Winds push material outward. Gravity pulls it inward. And within that interplay, the water vapour exists. Not still, not quiet, but part of an ongoing process, which makes it very different from the oceans we know. On Earth, oceans are relatively stable. They move, of course, through currents and tides, but their overall structure remains consistent over long periods. Here, stability is more temporary. The water is constantly being affected by changes in the environment. Regions may become denser or thinner. Temperatures may shift. Radiation levels may fluctuate. So instead of a calm body of water, it's more like a dynamic system, one that is always in motion, always adjusting, and yet, despite that constant activity, the overall reservoir persists, which is what allows us to describe it as an ocean at all. Now, there's something quietly fascinating about the idea that such an enormous amount of water exists in a place like this. because it challenges the way we usually think about water. We tend to associate it with planets, with surfaces, with places where it can collect and flow, but here it exists without any of that. No planet beneath it, no shoreline to contain it, just space. And that opens up a slightly different way of thinking. Water isn't limited to the kinds of environments we're familiar with. It can exist in a wide range of conditions as long as the basic ingredients are present and the environment allows it. And in the case of APM 08279 plus 5255, those conditions have aligned in a way that produces something truly large. Now, you might find yourself wondering what it would actually be like to encounter such a thing. Not in a literal sense, because the environment is far too extreme, but just as a way of picturing it. If you were somehow able to move through this region, you wouldn't see waves or reflections. You might not see anything at all, at least not in the way we're used to seeing. The water vapor would be invisible to the naked eye, but instruments would detect it. Sensors would pick up the presence of molecules, and if you could map it out, you'd see an enormous structure stretching across space, shaped by the forces around it. It's a kind of ocean that doesn't announce itself. It's not dramatic in appearance, but in scale, it quietly surpasses anything we know. And perhaps that's part of what makes it so intriguing. It's not immediately obvious. It doesn't look like an ocean. And yet, when you understand what's there, the amount, the extent, the context, it becomes something difficult to ignore. At some point, after hearing numbers like trillions of times larger than Earth's oceans, the mind tends to do something very natural. It pauses. Because numbers on that scale stop behaving in a way that feels intuitive. They become something you can repeat, but not quite something you can feel. So instead of trying to rush past that, it helps to slow down and approach the question gently. How big is the largest ocean in the universe? The one surrounding APM 08279 plus 5255, not just as a number, but as something we can gradually build an understanding of. Let's begin again with Earth, because it gives us a comfortable starting point. All of Earth's oceans combined contain about 1.4 billion cubic kilometers of water. That's already enormous. If you tried to imagine stacking that water into a cube, each side would stretch for over 1,000 kilometers. That's larger than many countries. Now imagine that cube, and then imagine making it bigger. Not 10 times bigger, not 1,000 times bigger, but 140 trillion times bigger. At this point, the image starts to dissolve a little, because there's no everyday experience that scales up in that way. We can't just keep adding more water in our minds and expect it to stay meaningful. So instead, it helps to shift perspective. Rather than thinking about a single container growing larger and larger, think about space itself, because that's where this ocean exists. The water around APM 08279 plus 5255 isn't gathered into a single body. It's spread across a region roughly hundreds of light years wide. Let's take a gentle step into that idea. A single light year, as we've mentioned, is the distance light travels in 1 year, about 9.5 trillion kilometers. So if you imagine traveling at the speed of light, something that for us is more of a thought experiment than a real possibility, it would still take hundreds of years to cross this region from one side to the other. Now place water throughout that space, not densely packed, not forming waves or surfaces, but existing as vapor, drifting among other gases. Each individual part feels sparse, but together, across that enormous volume, it adds up to something vast. It's a bit like trying to imagine the number of grains of sand on all the beaches of Earth. Except instead of grains, you're thinking about molecules, and instead of beaches, you're thinking about a region spanning light years. Now, there's another way to approach this, one that's a little less about numbers and a little more about comparison. If you took every ocean on Earth, every drop of water, and placed it inside this region, it would barely make a dent. It would be like adding a cup of water to a cloud that stretches across the sky. The scale difference is that extreme. And yet, despite that difference, the same basic molecule is present, H2O. 2 hydrogen atoms and 1 oxygen atom arranged in a very familiar way, which creates a quiet contrast. The smallest, simplest unit remains the same, but the total number of those units becomes almost beyond counting. Now, there's something else worth noticing here. When we talk about size, we often imagine something solid or clearly defined. A planet has a surface, a lake has a boundary, even a cloud has an edge, at least when we see it in the sky. But this cosmic ocean doesn't have a clear boundary in that sense. It gradually fades. The density changes from one region to another, becoming thinner as you move away from the central areas. So instead of thinking of it as a sharply defined object, it's better to think of it as a region where water is more concentrated than the surrounding space, a kind of zone. And within that zone, the total amount of water becomes enormous. Now, you might find yourself wondering how scientists actually estimate something like this. After all, they can't measure it directly. They rely on the light we talked about earlier. By studying how water molecules interact with radiation, absorbing and emitting specific wavelengths, astronomers can estimate how many molecules must be present to produce the observed signal. It's a bit like hearing a sound and inferring how many instruments are playing. You don't see each one individually, but you can build a picture from the overall pattern. And when they applied those methods to APM 08279 plus 5255, the conclusion was consistent. There was a vast amount of water, far more than anything we'd seen before, which is why it's often described as the largest known reservoir of water in the universe. Now here's where the scale becomes even more interesting, because it's not just about the amount of water, it's also about the environment in which that water exists. This isn't a quiet, isolated region. It's part of a system powered by a supermassive black hole, which means energy is constantly being added. Radiation is moving through the gas. Winds are shaping the distribution of material. So the size of this ocean isn't just a static feature. It's part of a dynamic system, one that changes over time, which makes the idea of how big it is a little more flexible. Because the boundaries can shift. The density can vary. The total amount of water may increase or decrease depending on the conditions. But even with that variability, the overall scale remains immense, and that's what stands out. Not just that it's large, but that it's large in a way that feels fundamentally different from anything we're used to. Now, there's a quiet question that sometimes arises when thinking about something like this. Does it even make sense to compare it to Earth's oceans? In one sense, yes. Because the comparison helps us grasp the magnitude. It gives us a reference point. But in another sense, the comparison also highlights how different the two are. Earth's oceans are dense, liquid, and contained. This cosmic ocean is diffuse, gaseous, and spread across space. So while the word ocean helps us begin to understand it, it also invites us to expand what that word can mean, to include not just the familiar image of water on a planet, but also the idea of water existing in entirely different forms and environments. And that shift in perspective is part of what makes this discovery so quietly compelling. It doesn't just add a new object to our list of things in the universe, it changes how we think about something we already know. Now, as we sit with that idea, the sheer size, the vast spread, the almost unimaginable quantity, there's a natural next step. Because numbers and comparisons can take us only so far. Eventually, we begin to wonder what this ocean actually looks like in relation to something closer to home. Not just in terms of scale, but in terms of experience. How does it differ from the oceans we know? And what does that difference tell us about the nature of water itself? Think for a moment about standing at the edge of the ocean on Earth. Not the whole planet, not the full map with its labelled basins and depths, just one quiet shoreline. The kind where the horizon stretches out in a straight, uninterrupted line, and the water seems to go on far longer than your eyes can comfortably follow. There's something grounding about that view. Even though the ocean is vast, your mind can still hold on to it. You understand, instinctively, that it has a surface. that it has a bottom somewhere far below, that it connects to other oceans, forming one continuous body of water that wraps around the planet. It feels large, but it also feels contained. Now, keeping that image gently in mind, let's place it beside what surrounds APM 08279 plus 5255, because this is where the comparison becomes both helpful and quietly misleading at the same time. On Earth, oceans are defined by boundaries. They sit in basins carved by geological processes. They are held in place by gravity, pulled toward the centre of the planet, forming a relatively thin layer when compared to Earth's overall size. Even the deepest trenches, impressive as they are, represent only a small fraction of the planet's radius. In other words, Earth's oceans are part of a surface. They have a clear down, a clear up, and a clear edge where water meets land or ice. The ocean around a PM 08279 plus 5255 has none of those things. There is no surface, no bottom, no coastline, no horizon in the usual sense. Instead, the water exists as a vast three-dimensional region, extending in all directions within a cloud of gas that spans hundreds of light years. It doesn't sit on anything. It doesn't pool. It doesn't flow downhill. It simply exists, suspended in space, shaped by gravity and radiation rather than by terrain. So right away, the comparison starts to stretch, but it doesn't break, because there are still ways in which the two can be meaningfully related. Let's begin with density. If you were to take a single litre of seawater from Earth and hold it in your hands, it would feel substantial, heavy, tangible. You could pour it, measure it, see it clearly. In contrast, the water vapour around APM 08279 plus 5255 is incredibly diffuse. Even in its densest regions, it would feel more like a near vacuum than anything resembling liquid. You could pass through it without noticing any resistance at all. So in terms of local experience, the two couldn't be more different. Earth's oceans are dense and immediate. The cosmic ocean is thin and almost imperceptible, and yet, when you zoom out, the picture changes. Because while Earth's oceans are dense, they're also relatively small in total volume compared to the vastness of space. The cosmic ocean, on the other hand, is spread across such an enormous region that its total amount of water becomes overwhelmingly large, even though any single part of it is sparse. It's a bit like comparing a single drop of ink in a glass of water to a faint mist that fills an entire valley. One is concentrated, the other is dispersed, but the total amount in the mist can be far greater, simply because it occupies so much more space. Now, let's gently shift to another aspect: temperature. On Earth, oceans exist within a fairly narrow temperature range. Even the coldest waters near the poles remain liquid due to the presence of salt and the pressure of the surrounding water. Life thrives in these conditions. Currents circulate heat. The system is dynamic but also balanced. Around APM 0827 9 plus 5255, the situation is very different. The water exists as vapour, at temperatures that would be considered extremely cold by everyday standards, yet relatively warm compared to the surrounding emptiness of space. More importantly, those temperatures are influenced by the intense radiation coming from the quasar, so instead of a stable thermal environment, you have something more variable. Energy flows through the region, heat is absorbed and emitted. The water is not part of a calm, self-regulating system, but part of a much larger, more energetic process. Still, despite those differences, there's a quiet connection, because in both cases, water is interacting with its surroundings. On Earth, it exchanges heat with the atmosphere, supports ecosystems, and participates in cycles like evaporation and precipitation. Near the quasar, it absorbs radiation, emits energy, and plays a role in the chemistry of the surrounding gas. Different scales, different conditions, but the same underlying molecule responding to its environment. Now, let's consider something else that often goes unnoticed: movement. When you think of Earth's oceans, you might picture waves, tides, currents. Motion is a defining feature. Water is constantly shifting, driven by wind, gravity, and the rotation of the planet. That movement is visible. You can watch it happen. In the cosmic ocean, movement exists as well, but it's not something you could observe directly with your eyes. Instead of waves, there are flows of gas. Instead of tides, there are gravitational influences. Instead of surface currents, there are large-scale motions shaped by radiation pressure and the pull of the black hole. It's movement on a scale that unfolds over vast distances and long periods of time. Subtle, gradual, but no less real. And once again, the comparison reveals both similarity and difference. Both systems involve motion, both are dynamic, but one is familiar and visible, while the other is distant and inferred. Now, there's one more aspect that gently ties these ideas together. Presence. Earth's oceans are central to life here. They cover most of the planet. They influence weather, climate, and ecosystems. They are something we experience directly, even if only occasionally. The ocean around a PM 08279 plus 5255 doesn't play that kind of role, at least not in any way we currently understand. There are no ecosystems there, no marine life, no cycles like the ones we depend on, and yet its presence still matters. Because it tells us something about the universe. It tells us that water, the same molecule that fills our oceans, can exist in places that are completely unlike Earth. It tells us that the ingredients for water were already widespread billions of years ago. And it tells us that scale in the universe can reach levels that feel almost disconnected from everyday experience. So when we compare these two oceans, one on Earth, one surrounding a distant quasar, we're not just comparing size, we're comparing contexts. One is part of a planet, shaped by geology and biology. The other is part of a galactic system, shaped by gravity and radiation. One is something we can stand beside. The other is something we can only study from afar through light that has travelled for billions of years. And yet, despite all of that, they share something fundamental. The same simple structure. The same combination of hydrogen and oxygen, which creates a quiet continuity. A reminder that even across enormous distances, even across different environments, some things remain consistent. Now, as this comparison settles, another question begins to form naturally. If the water around APM 08279 plus 5255 is so different from what we experience here, if it's not liquid, not visible, not something you could interact with directly, then what does it actually look like in its own environment? Not in terms of imagination alone, but in terms of its physical state. How does water behave under those conditions? What form does it take? And how does that form fit into everything we've been building so far? Picture a glass of water sitting quietly on a table. It's clear, reflective, contained. You can see its surface. Watch how it bends light. Notice how it moves if you tilt the glass just slightly. There's a familiarity to it, something your mind recognizes immediately without effort. Now, hold on to that image for just a moment, and then gently set it aside. Because water in deep space, especially in a place like the region surrounding APM 08279 plus 5255, looks nothing like that. In fact, if you were somehow able to be there, safely, with instruments designed to detect it, you might be surprised by what you don't see. There would be no shimmering surface, no waves, no reflections stretching toward a horizon. Instead, the water would be almost completely invisible. That might sound a little strange at first, because we're so used to water being something you can see and touch. But visibility depends on density and state, and in deep space, both of those are very different from what we experience on Earth. The water around APM 08279 plus 5255 exists primarily as vapour, not steam in the sense of a kettle boiling, thick and swirling, but an extremely diffuse gas. individual water molecules spread far apart, mixed with other gases, moving through space under the influence of gravity and radiation. If you were to take a small volume of that region, say something the size of a room, it might contain only a handful of water molecules, just a few, not nearly enough to form droplets or anything visible. And yet, when you extend that volume across hundreds of light years, the total number becomes enormous. So locally, it feels like almost nothing, but globally, it becomes one of the largest reservoirs of water ever observed. Now, this raises an interesting point. If it's so sparse, why do we still describe it as an ocean? And the answer comes back to scale again. Because what defines this ocean is not how dense it is in one place, but how much water exists overall across the entire region. It's a distributed presence rather than a concentrated one, more like a vast invisible fog than a body of liquid. Now, there's another layer to this that helps build a clearer picture. Even though the water itself is invisible, the environment around it is not entirely empty. The region contains dust, gas, and radiation. In some wavelengths, especially infrared and radio, this area can appear as a glowing cloud shaped by the energy coming from the quasar. So while you wouldn't see the water directly, you might see the structure it's part of. A faint, extended region of emission, stretching across space. Within that structure, the water molecules are there, interacting with radiation, absorbing and emitting energy in very specific ways, and that's how we detect them, not by seeing them as droplets or vapor clouds, but by observing how they affect light. Now let's gently explore the state of this water a bit more. On Earth, water can exist as a solid, liquid, or gas, depending on temperature and pressure. Ice, liquid water, and vapor. In deep space, especially in regions like this, liquid water is extremely rare. There's simply not enough pressure to hold molecules together in that form, so water tends to exist either as ice, frozen onto dust grains, or as vapor, moving freely as individual molecules. Around APM 08279 plus 5255, the conditions favour vapor. The environment is warm enough and energetic enough to keep the water from freezing. At the same time, it's not dense enough for liquid to form. So the water remains in this gaseous state, drifting through the region, and while that might sound less impressive than an ocean of liquid water, it's actually just as significant, if not more so. Because it shows that water can exist under a wide range of conditions. It doesn't need a planet, it doesn't need oceans or lakes. It can exist in the open space between stars, as long as the right elements are present and the environment allows it. Now, here's something quietly interesting. Even though the water is invisible, it still interacts with light in very precise ways. Each molecule can absorb energy at specific wavelengths, causing electrons and rotational states to change. Then, as the molecule returns to a lower energy state, it emits radiation. These interactions create the spectral signatures that astronomers detect, so in a sense the water reveals itself through its behaviour, rather than through its appearance. It's not something you see, it's something you infer, something you understand by reading the patterns it leaves behind, and that's a recurring theme in astronomy. Much of what we know about the universe comes not from direct images, but from careful interpretation of light. Now let's take a moment to imagine moving through this region again, not physically, but conceptually. You're not surrounded by water in the way you would be underwater on Earth. There's no pressure, no resistance, no sense of being immersed. Instead, you're moving through space that contains traces of water. Molecules passing by, too far apart to notice individually but collectively forming part of a much larger structure. It would feel empty, and yet it wouldn't be truly empty. There would be particles, radiation, energy flowing through the region, and within that, the water exists, quietly, subtly. Now, there's also something worth noting about how this water is distributed. It's not uniform. Some regions contain more molecules than others. There are variations in density, temperature, and radiation levels. These variations create a kind of structure within the cloud, areas where conditions are slightly different, where molecules may be more concentrated or more active. So instead of a smooth, uniform ocean, it's more like a patchwork. A complex environment with different regions interacting with each other. And that complexity is part of what makes it so interesting to study, because it gives scientists clues about the processes at work, how gas moves, how molecules form, how energy is transferred. Now, bringing this gently back to something familiar, it's almost like comparing a clear sky to a foggy one. In a dense fog, you can see the water droplets. They scatter light, creating a visible mist. In a clear sky, the water vapor is still there, but it's too diffuse to see. The cosmic ocean is closer to that clear sky, but stretched across an unimaginable scale, which is why it feels both present and absent at the same time. Now, as we sit with that idea, invisible water, spread across space, interacting with radiation, forming part of a dynamic system, there's a natural next question that begins to take shape. Because while we've described what it looks like, or rather what it doesn't look like, we haven't yet fully explored the conditions that allow it to exist in that form. What kind of temperatures are we dealing with? What kind of pressures? What kind of environment allows water to remain as vapor in such a vast region? And how do those conditions compare to anything we know here on Earth? Step outside on a cool evening and take a slow breath. The air feels light, maybe a little crisp, but it's there. You can feel it against your skin, notice its temperature, sense the gentle pressure of the atmosphere surrounding you. Even without thinking about it, your body is constantly interacting with those conditions, adjusting, balancing, staying comfortable within a very narrow range. Now imagine removing almost all of that, not lowering the pressure slightly, not cooling the air a bit more, but taking it down to something so thin that it barely qualifies as an environment at all. That's where we begin when we talk about the conditions surrounding APM 08279+5255. Because while we've been describing this vast ocean of water, the setting it exists in is nothing like the environments we experience on Earth. Let's start with temperature. When people hear the word space, they often think of it as extremely cold. And in many regions, that's true. The average temperature of the universe is just a few degrees above absolute zero, colder than anything naturally found on Earth. But near a quasar, things are a bit more complicated. The region around APM 08279+5255 is filled with radiation, energy streaming outward from the accretion disk around the central black hole. This energy interacts with the surrounding gas, heating it to temperatures that, while still cold by everyday standards, are relatively warm compared to the emptiness of space. The water vapor in this region exists at temperatures of roughly -63 degrees Celsius. Now that might sound extremely cold, and in everyday terms it is. It's colder than the coldest natural temperatures recorded on Earth's surface. But in the context of space, it's actually quite moderate. It's warm enough to keep water from freezing into ice, yet not so hot that the molecules are completely broken apart by energy. So right away you can see that the conditions are finely balanced. Too cold, and the water would freeze onto dust grains, becoming solid. Too hot, and the molecules would be destroyed, breaking into hydrogen and oxygen. But here, the temperature sits in a range where water can exist as vapor, which brings us to pressure. On Earth, pressure is something we rarely think about, but it plays a crucial role in determining how substances behave. At sea level, the pressure of the atmosphere allows water to exist as a liquid over a wide range of temperatures. It holds molecules close together, giving water its familiar properties. In deep space, that pressure is almost entirely absent. The density of gas around APM 08279+5255 is higher than the average interstellar medium, but it's still incredibly low compared to Earth's atmosphere. If you were to compare it directly, the pressure would be trillions of times lower than what you experience standing on the surface of our planet. So under those conditions, liquid water simply can't exist. There's not enough pressure to keep molecules close together. Instead, water exists as individual molecules, moving freely, occasionally interacting but never forming a continuous liquid. This is why the ocean we've been describing is not liquid at all. It's entirely gaseous. Now here's where things become quietly interesting. Even though the pressure is extremely low, it's not zero. There is still enough density for molecules to encounter each other, to collide, to interact. And those interactions matter, because they allow for chemical reactions to take place. They allow for energy to be transferred, and they allow for structures, however diffuse, to form over time. So instead of thinking of this region as empty, it's more accurate to think of it as sparse but active, a place where particles are few, but still part of a larger system. Now let's bring temperature and pressure together for a moment. On Earth, the relationship between these two factors determines whether water is solid, liquid, or gas. There's a familiar diagram, often called the phase diagram of water, that shows how different combinations of temperature and pressure lead to different states. In deep space, conditions fall into a part of that diagram where liquid water simply isn't stable. The pressure is too low, so even if the temperature were right, the molecules wouldn't stay together. They would spread out, becoming vapor, which is exactly what we see around APM 08279 plus 5255. But temperature and pressure aren't the only factors at play. There's also radiation. And in this environment, radiation is a constant presence. The quasar at the centre emits enormous amounts of energy across the electromagnetic spectrum. Some of that energy reaches the surrounding gas, including the water vapour. And when it does, it can excite the molecules, raising their energy levels, causing them to emit radiation of their own. This process is part of what allows astronomers to detect the water in the first place. But it also affects the stability of the molecules. High-energy radiation can break chemical bonds. So for water to survive, there must be regions where the radiation is not overwhelming, where gas and dust provide some level of shielding, where the energy is enough to keep the molecules active but not enough to destroy them. And once again, we find that delicate balance. Not too much, not too little, just enough for water to exist. Now there's another aspect of this environment that's worth considering. Motion. Everything in this region is moving. Gas is flowing inward toward the black hole. Radiation is pushing outward. Winds are carrying material across vast distances. And within that motion, the water molecules are constantly being transported. They're not fixed in place. They drift. They mix. They become part of different regions over time. So instead of a stable body, we have a dynamic system. One where conditions change, sometimes gradually, sometimes more dramatically. And yet, over large scales, the overall structure persists. The reservoir of water remains. Now, there's something quietly remarkable about that persistence, because it suggests that even in a highly energetic environment, where forces are constantly at work, certain patterns can endure, certain molecules can remain present, and that speaks to the resilience of water as a molecule. It's simple, just 2 hydrogen atoms and 1 oxygen atom, but that simplicity makes it versatile. It can exist under a wide range of conditions, from the deep cold of space to the heat of planetary atmospheres, from icy comets to gaseous clouds near quasars, and that versatility is part of why it appears in so many places throughout the universe. Now bringing all of this together, temperature, pressure, radiation, motion, we begin to see the environment around APM 08279 plus 5255 as something more than just a distant curiosity. It becomes a system with its own internal logic, a set of conditions that, while very different from Earth, still follow the same physical principles, the same rules of chemistry and physics, just applied on a much larger scale, and within that system, water finds a way to exist, not as we know it, not in a form we could interact with directly, but as part of a vast dynamic structure that stretches across space. Now that we understand the conditions, the temperature, the pressure, the energy, it becomes easier to ask a more practical question. How do scientists actually detect something like this? How do they find water that can't be seen in a place that's billions of light years away? What tools do they use, and how do those tools turn faint signals into meaningful discoveries? Long before anyone could speak about oceans in distant galaxies, astronomers had already learned something important. Space does not reveal its secrets easily, not because it is trying to hide anything, but because most of what exists out there doesn't behave in ways our eyes are designed to notice. Light, as we experience it, is only a very small part of a much larger spectrum, and many of the most interesting signals in the universe exist completely outside of what we can see. So when scientists talk about detecting water around APM 08279 plus 5255, they are not describing a direct observation. There is no image where you can point and say, there it is, that's the water. Instead, what they're doing is something quieter. They are listening. Not with ears, of course, but with instruments designed to pick up patterns in light, especially light that our eyes cannot detect. And to understand how that works, it helps to start with a simple idea. Every molecule has a kind of signature, not a visual shape, not something you can photograph directly, but a pattern in the way it interacts with energy. Water molecules, for example, can rotate and vibrate in very specific ways. When they do, they absorb and emit radiation at very precise wavelengths. Think of it a bit like a musical instrument. Each instrument produces its own set of tones, even when playing the same note. A violin and a piano might both play middle C, but they sound different because of how the vibrations are structured. In a similar way, different molecules sound different when they interact with radiation, and astronomers have learned how to recognize those sounds. Now, the kind of radiation we're talking about here is not visible light. It's mostly in the infrared and radio parts of the spectrum. These wavelengths are longer than visible light, which means they carry less energy, but they are incredibly useful for studying cold, distant objects. Water vapor in particular has strong signatures in the infrared and submillimeter range. So when astronomers want to detect water in space, they use telescopes that are sensitive to those wavelengths. Not the kind of telescope you might imagine looking through with your eye, but large, highly specialized instruments. One of the key tools for studying distant molecules like this is a radio telescope. Instead of collecting visible light, radio telescopes detect radio waves, a form of electromagnetic radiation with much longer wavelengths. These telescopes can be enormous. Sometimes they consist of single large dishes. Other times they are arrays of many smaller dishes working together, spread out over large distances. By combining signals from multiple telescopes, astronomers can create very detailed observations, even of objects that are billions of light years away. Now, when a telescope is pointed towards something like APM 08279 plus 5255, it collects the radiation coming from that direction. But that radiation is not just a simple signal, it's a mixture. Light from the quasar itself, light that has passed through surrounding gas, light that has been absorbed and re-emitted by various molecules. So the first step is to separate that mixture, to break the incoming radiation into its component wavelengths. This process is called spectroscopy, and it's one of the most powerful tools in astronomy. When the light is spread out into a spectrum, it reveals patterns, tiny dips where certain wavelengths have been absorbed, small peaks where energy has been emitted. Each of those features corresponds to specific transitions in atoms or molecules, and among those features, astronomers can identify the signature of water. Now here's where things become a little more intricate, because the signal from APM 08279 plus 5255 is incredibly faint. It has travelled for billions of years, spreading out as it goes. By the time it reaches Earth, only a tiny fraction of the original radiation remains, so detecting it requires not only sensitive instruments, but also careful analysis. Astronomers often observe the same object multiple times, using different telescopes, different wavelengths, different methods. They compare results. They look for consistency. They rule out alternative explanations. Because at these distances, it's important to be certain. A small error could lead to a completely different conclusion. But in this case, the evidence held up. The spectral lines match those of water vapour. Repeated observations confirmed the signal, and once that was established, scientists could move on to the next step, estimating how much water was present. Now, this is not as simple as counting molecules. Instead, it involves modelling. By looking at the strength of the spectral lines, how much radiation is being absorbed and emitted, astronomers can infer the number of molecules required to produce that signal. It's a bit like hearing a crowd from a distance and estimating how many people are there based on the volume of the sound. You don't see each individual, but you can make a reasonable estimate. In the case of APM 08279 plus 5255, those estimates led to the conclusion that there is an enormous amount of water vapour, far more than anything we've observed elsewhere. And that's how something invisible becomes measurable, through patterns, through signals, through careful interpretation of light. Now there's another subtle aspect to this process that's worth noticing, because the light we receive doesn't just carry information about what is present, it also carries information about motion. When a source of light is moving relative to us, its wavelengths shift slightly. This is known as the Doppler effect. If something is moving away, the wavelengths stretch, shifting toward the red end of the spectrum. If it's moving closer, they compress, shifting toward the blue. By analysing these shifts, astronomers can learn how gas is moving within the region, whether it's flowing inward, outward, or rotating. And in the case of APM 08279 plus 5255, these measurements reveal a dynamic environment. Gas moving under the influence of gravity and radiation, water vapour being carried along with it. So not only do we detect the presence of water, but we also gain insight into how it behaves within that system. Now, all of this might sound quite technical, but at its core, the idea is surprisingly simple. Light carries information. If you can read that information carefully enough, you can learn about things that are far beyond direct observation. And that's what makes this discovery so quietly remarkable. Because no one has ever been to APM 08279 plus 5255, no probe has visited it, no direct image shows its structure in detail, and yet, through the study of light, we know that there is water there. We know roughly how much. We know the conditions it exists in, all from signals that have travelled across billions of years. Water is not unique in this sense. It's one of many molecules that exist in space. Hydrogen, carbon monoxide, ammonia, methane, all of these have been detected in various regions of the universe, which leads to a broader thought. If water can exist in such an extreme environment, and if we can detect it from such a distance, what does that say about molecules in general? How common are they? How do they form? And how do they survive in places that seem at first glance too harsh for complex chemistry? Long before telescopes became powerful enough to study distant quasars, there was a simpler assumption about space, that it was mostly empty. Not just quiet or dark, but chemically simple. A vast expanse filled mainly with hydrogen and helium, the two lightest elements, drifting apart as the universe expanded. And for a time, that assumption made sense. Right after the Big Bang, the universe really was dominated by those elements. Hydrogen formed first, followed by helium, and only trace amounts of anything heavier existed in those early moments. But the universe doesn't stay simple for long, because stars begin to form, and once stars exist, everything starts to change. Inside stars, nuclear fusion takes place. Hydrogen is fused into helium, helium into heavier elements, and over time, stars begin to produce things like carbon, nitrogen, oxygen, and beyond. When those stars reach the end of their lives, especially the more massive ones, they release those elements back into space. Sometimes gently, through stellar winds, sometimes violently, through supernova explosions. Either way, the result is the same. Space becomes enriched, and once you have a mix of different elements drifting through space, something quietly interesting begins to happen. Chemistry. Which brings us back, in a broader sense, to the environment around APM 08279 plus 5255. Because the presence of water there is not an isolated event. It's part of a much larger pattern. Molecules, not just simple atoms, exist all across the universe, and they form in places that at first glance might not seem suitable at all. Now, if you imagine molecules forming, you might picture something like a laboratory. Controlled conditions, stable temperatures, precise interactions. But in space, the process is far more subtle and far more patient. Molecules form in regions where gas becomes slightly denser than average. These regions are often called molecular clouds. They are cold, relatively speaking, and shielded from intense radiation by dust and other material. Within these clouds, atoms can come together, slowly, occasionally, not in rapid, constant reactions, but in rare encounters that, over long periods of time, add up. A hydrogen atom meets an oxygen atom, they bond, and with the addition of another hydrogen atom, water forms. Now this might sound like a simple process, but in space, even simple processes can take thousands or millions of years. There's no rush, no urgency, just gradual accumulation. And over time, entire regions become rich in molecules: water, carbon monoxide, methane, ammonia, and many others. Some of these molecules are quite complex. Organic molecules containing carbon have been detected in various parts of the universe. Not life, of course, but the building blocks that, under the right conditions, could eventually lead to more complex chemistry, which creates an interesting connection, because the same basic ingredients that exist in distant molecular clouds are also found here on Earth. The difference is not in the components, but in the environment. On Earth, those components are brought together under conditions that allow for liquid water, stable temperatures, and long-term chemical interactions. In deep space, the same components exist, but in very different states, more spread out, more influenced by radiation, more dependent on large-scale processes like star formation and galactic dynamics. Now, when we look at APM 08279 plus 5255, we're seeing an environment that is more energetic than a typical molecular cloud. There's radiation from the quasar, there's motion driven by gravity, there are winds and flows of gas, and yet, within that environment, molecules still exist. Which tells us something important. Molecules are more resilient than we might expect. They can form and survive in a wide range of conditions, as long as there are regions where the balance is right. Not too much radiation, not too little density, just enough for interactions to occur, and once those molecules are present, they become part of the larger system. They move with the gas, they interact with radiation, they contribute to the overall structure of the region. Now, there's another layer to this that quietly expands the picture. Because molecules don't just exist in isolated clouds, they are found in many different environments. In the atmospheres of planets, in the disks around young stars where planets are forming, in comets and asteroids, even in the space between galaxies in certain conditions. So when we detect water around APM 08279 plus 5255, we're not seeing something completely unique. We're seeing an extreme example of something that is, in a broader sense, quite common. Water is one of the most abundant molecules in the universe. Not everywhere, not in equal amounts, but present in many places, and that has interesting implications, because water plays a central role in chemistry. It acts as a solvent, it facilitates reactions, it helps transport energy and matter. On Earth, it's essential for life. In space, it's part of the chemical network that shapes how matter evolves. Now, it's important to be careful here. The presence of water does not mean the presence of life. The environment around a quasar is far too extreme for anything like life as we know it. But the existence of water does suggest that the building blocks for more complex systems are widespread, which brings a quiet sense of continuity. From distant quasars to molecular clouds to planets like Earth, the same basic ingredients appear again and again: hydrogen, oxygen, carbon, nitrogen, arranged in different ways, under different conditions, producing different outcomes. Now, let's gently return to the idea of scale, because while molecules are common, the sheer quantity of water around a PM 08279 plus 5255 is not. It represents an extreme case, a place where the processes that form molecules have led to an enormous accumulation, and that makes it a valuable object of study. Because by understanding how molecules behave in such an environment, scientists can refine their models. They can learn more about how gas cools, how radiation interacts with matter, how chemical reactions proceed under different conditions, all of which helps build a more complete picture of the universe. Now, there's something quietly reassuring about this. Even in the most distant and energetic regions, the same basic rules apply. The same physics, the same chemistry, the same interactions between particles. It's just that the scale changes, the context changes, but the underlying principles remain consistent. Now that we've explored how molecules exist across the universe, and how water fits into that broader picture, it becomes interesting to look at the timing of all of this. When did these molecules form? How early in the universe's history did water begin to appear? And what does that tell us about the evolution of cosmic structures over time? Imagine for a moment a time when the universe was far simpler than it is now. Not quieter, not necessarily calmer, but simpler in what it contained. No planets, no oceans, no complex chemistry drifting through space. Just a hot, dense beginning that gradually expanded and cooled. In those earliest moments after the Big Bang, the universe was almost entirely made of hydrogen and helium. Nothing more complicated, no oxygen yet, no carbon, no nitrogen, which means, quite simply, no water. So when we look at something like APM 08279 plus 5255 and find vast amounts of water surrounding it, we're not just observing a distant object. We're seeing the result of a long chain of events, a process that began with simplicity and slowly, patiently, built complexity over time. Now that process starts with stars, because stars are the factories where heavier elements are created. Inside a star, hydrogen atoms fuse together to form helium. As the star evolves, especially if it's large enough, it begins to fuse heavier and heavier elements. Helium becomes carbon. Carbon can lead to oxygen. And in the most massive stars, this chain continues, producing a wide range of elements that didn't exist at the beginning of the universe. But these elements don't stay locked inside the star forever. Eventually, the star reaches the end of its life, and depending on its size, it may release its outer layers gently, or it may explode in a supernova, scattering its contents across space. And when that happens, the surrounding region becomes enriched. Gas that was once mostly hydrogen and helium now contains oxygen, carbon, and other elements, which creates the conditions needed for molecules to form, including water. Now here's where the timing becomes interesting. A PM 08279 plus 5255 is so distant that we are seeing it as it was billions of years ago, when the universe was still relatively young. That means all of these processes, star formation, element creation, and molecule formation, must have already taken place by that time, and not just once, but on a scale large enough to produce the enormous reservoir of water we've been discussing. So what does that tell us? It tells us that the universe didn't take too long to start building complexity. Within a few billion years, stars had already formed, lived their lives, and enriched their surroundings with heavier elements. And those elements had already begun to combine into molecules, including water, which suggests that the ingredients for water, and by extension, the ingredients for more complex chemistry, were available relatively early in cosmic history. Now, it's worth pausing here for just a moment, because this idea quietly shifts the way we think about the universe. It's easy to imagine the early universe as something simple for a very long time, but observations like this show that it evolved more quickly than we might expect. Not instantly, of course. Everything still unfolded over vast stretches of time, but in cosmic terms, the transition from simplicity to complexity happened sooner than one might assume. Now, let's gently connect this back to the environment around APM 08279 plus 5255. The water we detect there didn't appear out of nowhere. It is the result of earlier generations of stars that formed, produced oxygen, and released it into the surrounding gas. Hydrogen, already abundant, combined with that oxygen under the right conditions, and over time, large amounts of water vapor accumulated. So when we observe that region, we're not just seeing a quasar and its surroundings, we're seeing a record of earlier events, a kind of layered history where each stage builds on the one before it. First, the formation of stars, then the creation of heavier elements, then the formation of molecules, and finally, the accumulation of those molecules into large-scale structures. Now there's another subtle point here that often goes unnoticed. The presence of water also tells us something about the temperature and density conditions in the early universe. Because for water to form and survive, the environment must allow it. That means there must be regions where gas can cool, where radiation is not overwhelming, where molecules can exist long enough to be detected, and the fact that we see water in such large quantities suggests that these conditions were not rare. They existed in at least some regions, even relatively early on. Now this doesn't mean the entire universe was filled with water at that time, far from it. Conditions varied widely from place to place. Some regions were too hot, others too sparse, but in certain areas, like the one surrounding APM 08279 plus 5255, the balance was just right, and that allowed water to become a significant component of the environment. Now, there's something quietly fascinating about the idea that water, something so central to life on Earth, has roots that go back to such early stages of the universe. It's not something that only appeared recently. It's part of a much longer story, a story that began with the first stars and continued through countless generations of stellar evolution, which brings a gentle sense of continuity. The water we drink, the oceans we see, the clouds in the sky, all of it is connected in a distant way to processes that began billions of years ago. Now, of course, the water around APM 08279 plus 5255 is not part of that direct lineage. It exists in a different region under very different conditions, but it shares the same origin, the same basic process of element formation and molecular assembly, and that connection is enough to make the comparison meaningful. Now, as we sit with this idea that water existed in large quantities even when the universe was young, there's a natural question that begins to take shape. If the ingredients for water were already present, and if the conditions allowed it to form, could similar processes lead to something more complex? Could environments like this, or others less extreme, support the kinds of chemistry that eventually lead to life? Let's take this idea slowly, because it's one of those questions that sounds simple at first, but becomes more layered the longer you sit with it. Could life ever exist in a place like the environment surrounding APM 08279 plus 5255? At first glance, the instinctive answer is no, and not in a dramatic or dismissive way, just in a practical sense. The conditions we've been building up, the intense radiation, the extremely low density, the absence of liquid water, the constant motion of gas, all of these factors create an environment that is very far removed from anything we associate with life on Earth. But instead of stopping there, it helps to slow down and examine why that answer feels so immediate. Because when we talk about life, we're usually thinking about something quite specific. Life as we know it. Organisms that rely on liquid water. Chemical reactions that take place within stable temperature ranges. Structures that require a certain level of pressure to hold together. Energy sources that are steady enough to support long-term processes. On Earth, all of these conditions come together in a very particular way. Water exists as a liquid across large regions of the planet. The atmosphere provides pressure, the sun provides a relatively stable source of energy, and over billions of years life has adapted to those conditions. So when we look at a place like APM 08279 plus 5255, the contrast becomes clear. There is no surface, no oceans in the liquid sense, no stable environment where molecules can gather into complex structures and remain intact over long periods. Instead, there is motion, radiation, extremely low density. Water exists but only as vapor, spread thinly across vast distances, and under those conditions, the kinds of chemical processes that support life as we know it become very difficult. Not impossible in a purely theoretical sense, but highly unlikely. Now that's the straightforward part of the answer. But there's another way to approach the question, one that doesn't stop at what we already know, because the universe has a way of being more varied than our expectations. So instead of asking whether life like ours could exist there, we might ask a slightly different question. Could any form of life exist in such an environment? And that's where things become more uncertain. Not because there is evidence that life exists near quasars, there isn't, but because our understanding of life is based on a single example, Earth. We know what works here. We know the conditions that support biology as we experience it, but we don't yet know the full range of possibilities. Could life exist without liquid water? Could it operate at extremely low densities? Could it use energy in forms we don't typically associate with biological processes? These are open questions. And while most current scientific thinking suggests that environments like the one around APM 08279 plus 5255 are too extreme, it's still useful to explore the reasoning behind that conclusion. Let's start with water again, but from a different angle. Water is often described as essential for life, not just because it's present in living organisms, but because of what it does. It acts as a solvent. It allows molecules to move, to interact, to react with each other. It helps regulate temperature. It supports complex chemistry. In its liquid form, water creates an environment where reactions can occur efficiently and consistently. In the vapor form, especially at very low densities, those advantages largely disappear. Molecules are too far apart. Interactions are too rare. There's no medium to facilitate the kind of sustained chemistry that life depends on. So even though water is present around APM 08279 plus 5255, it doesn't play the same role it does on Earth. Now, let's consider energy. Life requires energy, but not just any kind. It needs energy that can be harnessed in a controlled way. On Earth, that energy often comes from the sun, or from chemical gradients, or from geothermal sources. In the environment around a quasar, energy is abundant. In fact, there's more than enough of it. But it's not the kind of energy that is easily controlled. Radiation from the accretion disk is intense and variable. High-energy photons can break chemical bonds, disrupting molecules rather than supporting their formation. So instead of providing a stable energy source, the environment tends to be disruptive. Now let's think about structure. Life, as we know it, depends on organized structures, cells, membranes, molecules arranged in specific ways. These structures require a certain level of stability. They need to persist long enough for processes to take place. In a region where gas is constantly moving, where densities are extremely low, and where radiation is strong, maintaining such structures becomes very difficult. There's nothing to hold them together, nothing to protect them from the surrounding conditions, so even if complex molecules were to form, they would likely be short-lived. Now, there's another aspect to consider, and that's time. Life doesn't appear instantly. It develops over long periods. It requires stability, consistency. Environments where conditions remain within certain ranges for extended durations. The region around APM 08279 plus 5255 is dynamic. Conditions change, gas flows, radiation fluctuates. It's not the kind of place where long-term stability is easily maintained, which further reduces the likelihood of life developing there. Now, all of this might make the answer feel quite definitive. No, life as we understand it is extremely unlikely in such an environment, and that's a reasonable conclusion. But there's still something interesting about the question itself, Because even if the answer is no, exploring why helps us understand what life requires. It highlights the importance of certain conditions: liquid water, moderate temperatures, sufficient pressure, stable energy sources, and in doing so, it also helps us identify where in the universe those conditions might exist. Not near quasars perhaps, but in other regions, around stars, on planets, within more stable environments. Now, there's also a quieter perspective to consider. Even if life cannot exist there, the presence of water still matters, because water is part of the broader chemical landscape of the universe. It participates in reactions, it contributes to the formation of other molecules, it plays a role in the evolution of matter. So while it may not support life in that specific location, it's still part of the chain of processes that, elsewhere, can lead to life, and that connection is worth noticing, because it ties together very different parts of the universe, from extreme environments near black holes to more familiar settings like planets and oceans, all linked by the same basic chemistry. Now there's one more subtle point that often emerges when thinking about this question: the idea of limits. We tend to define the boundaries of life based on what we observe, but those boundaries are not fixed. On Earth, life exists in places that were once thought to be uninhabitable, deep under the ocean, in extremely hot environments, in highly acidic conditions, in places with very little light. These examples show that life can adapt to a wide range of conditions, but even those extremes have limits, and the environment around APM 08279+5255 appears to lie beyond those limits, at least based on what we currently understand. So while it's always possible that new discoveries could expand our view, the balance of evidence suggests that this is not a place where life would thrive, and perhaps that's okay. Because not every part of the universe needs to support life in order to be interesting. Some regions are important because they show us what is possible, how matter behaves under extreme conditions, how molecules form and persist, how energy flows through large systems, and in that sense the ocean around APM 08279+5255 is still deeply meaningful, not as a habitat, but as a phenomenon. A reminder that water, something we associate so strongly with life, can also exist in places where life itself is unlikely, which adds a kind of contrast, a separation between the presence of ingredients and the presence of outcomes, and that contrast helps sharpen our understanding of both. If water can exist in such an extreme environment, even without supporting life, it raises a broader question. What role does water play across the universe as a whole, not just in specific locations but in the larger picture? How common is it? How does it influence the formation of structures? And what does it tell us about the nature of the cosmos itself? Consider how often water appears in the story we've been building. It shows up on Earth in oceans, lakes, clouds, and ice. It appears in comets drifting through the outer solar system. It exists on distant moons, locked beneath icy surfaces or hidden in thin atmospheres. And then, unexpectedly, it appears around something as extreme as APM 08279+5255, stretched across hundreds of light years. That pattern is not random. Water is not a rare exception in the universe. It is in many ways one of its most persistent and adaptable molecules. And understanding its role means stepping back a little from any single location and looking at the broader picture. Because water does not just exist, it participates, it influences processes, it becomes part of how matter behaves over time. Let's begin with something simple. Water is made of hydrogen and oxygen. Hydrogen, as we've mentioned before, is everywhere. It's the most abundant element in the universe. Oxygen, while less common, is still widely produced inside stars and distributed through space as those stars evolve and eventually release their material. So the ingredients for water are not unusual. They are part of the natural outcome of stellar evolution, which means that wherever you have enough hydrogen, enough oxygen, and the right conditions, water can form. Now that might sound straightforward, but what makes water particularly important is not just that it forms easily, but how it behaves once it exists. Water has a set of properties that make it especially effective at interacting with its surroundings. For one thing, it can absorb and emit radiation in specific ways. This might sound like a small detail, but it has significant consequences. In regions where gas is cooling, water can act as a kind of regulator. It can carry energy away, allowing the gas to lose heat more efficiently. And when gas cools, it can collapse under gravity more easily. That collapse is what leads to the formation of stars, so in a quiet way, water can influence how stars form. Not as the primary driver, but as part of the overall process. It contributes to the cooling of gas clouds, helping them reach the conditions needed for gravitational collapse. Now let's connect that back to the larger structures in the universe. Stars form inside molecular clouds. Those clouds contain a mixture of gases and molecules, including water. As regions within the cloud cool and contract, they eventually give rise to new stars. Around those stars, disks of material can form, and within those disks, planets may begin to take shape. So water is present at multiple stages of this process, in the clouds where stars form, in the disks where planets form, and sometimes, eventually on the surfaces of those planets, which creates a kind of continuity, from large-scale structures down to smaller, more familiar environments. Now, it's important to be careful here. Water is not the only molecule involved in these processes. There are many others: carbon monoxide, ammonia, methane, and more. Each of them plays a role, but water stands out because of how common it is and how strongly it interacts with radiation, which makes it easier to detect and easier to study. Now let's shift gently to another aspect: water as a tracer. In astronomy, certain molecules are used as indicators of conditions within a region. By detecting them, scientists can learn about temperature, density, and motion. Water is particularly useful in this regard, because its spectral signatures are well understood. When astronomers detect water vapor in a region, they can use that information to estimate how warm the gas is, how dense it might be, and how it is moving. So water becomes more than just a component. It becomes a tool, a way of reading the environment. And this is especially important in distant objects like APM 08279 plus 5255. Because we can't observe those regions directly. We rely on signals, on patterns in light. And water helps provide those patterns. Now, there's another role water plays, one that is perhaps more familiar: its connection to life. On Earth, water is essential. It supports biological processes. It allows for complex chemistry. It provides a medium where reactions can occur efficiently. So when scientists find water elsewhere in the universe, it naturally draws attention. Not because it guarantees life, but because it suggests that one of the key ingredients is present. But as we've discussed, the presence of water alone is not enough. The conditions must also be right. Liquid water, moderate temperatures, sufficient pressure, and stable environments are all important. So while water is a necessary component for life as we know it, it is not sufficient on its own. And in places like the region around APM 08279 plus 5255, those additional conditions are not present. Still, the presence of water in such an extreme environment tells us something important. It tells us that water can exist under a wide range of conditions, which increases the number of places where it might be found, and by extension, the number of places where life might eventually arise, under the right circumstances. Now let's return briefly to scale. Because the amount of water around APM 08279 plus 5255 is so large that it emphasizes just how widespread this molecule can be. Not just present, but abundant. And that abundance suggests that water is not a rare outcome. It's a common product of the processes that shape the universe, which leads to a quiet shift in perspective. Instead of thinking of water as something unique to Earth, we begin to see it as part of the broader fabric of the cosmos, something that appears wherever conditions allow, something that connects different environments, from the cold of interstellar space to the warmth of planetary surfaces. Now there's one more aspect to consider: water as part of cycles. On Earth, water moves through cycles: evaporation, condensation, precipitation, flow. It's constantly changing state and location. In space, the cycles are different, but the idea still applies. Water can form on dust grains in cold regions. It can be released into the gas phase when those grains are heated. It can be incorporated into comets and asteroids. It can be delivered to planets. It can be broken apart by radiation and reformed again. So even in the vastness of space, water participates in processes that move it from one form to another, from one location to another, and over long periods of time, those processes shape where water ends up. Now, bringing all of this together, the role of water in the universe becomes clearer. It is not just a passive substance. It is an active participant in the evolution of matter. It influences how gas cools. It helps trace conditions in distant regions. It contributes to the formation of stars and planets. And in certain environments, it supports life, even in places where life is unlikely, like the region around APM 08279 plus 5255. Water still plays a role. It interacts with radiation. It becomes part of the chemical landscape. It helps us understand what is happening in those distant systems. If you take a quiet look at the night sky, it can feel like everything is neatly separated. Stars appear as points, planets as brighter points, galaxies, if you're in a dark enough place, as faint smudges. It gives the impression that space is organized into clear, distinct objects with empty gaps in between. But that impression is a little misleading, because between those visible points, and even around them, there is structure. Not always obvious, not always visible in the usual sense, but very much present. And when we begin to look at environments like the region surrounding APM 08279 plus 5255, that hidden structure becomes essential to understanding everything we've been discussing. Because the water we've been talking about does not exist on its own. It is part of something larger, a vast arrangement of gas, dust and energy that forms what astronomers often call a cloud, though the word cloud here doesn't quite match the kind you might see drifting across the sky on Earth. Still, it's a useful starting point. So let's begin there, gently, and then expand the idea. On Earth, a cloud is made of tiny droplets of water or ice, suspended in the air. You can see it because those droplets scatter light. It has a shape, though it changes over time. It moves with the wind. In space, a cloud is similar in concept, but very different in detail. Instead of droplets, you have atoms and molecules. Instead of dense air, you have extremely low-density gas. Instead of a clearly visible boundary, you have gradual transitions, regions where the density slowly changes from one place to another. And instead of being a few kilometers across, these clouds can stretch for dozens, hundreds, or even thousands of light years. Now in the case of APM 08279 plus 5255, the ocean of water exists within one of these extended structures, a region of gas that is influenced by the quasar at its centre, which means that the cloud is not just sitting there quietly. It is part of a dynamic system. Gas is moving, energy is flowing, radiation is interacting with matter, and within all of that, structures begin to emerge. Not rigid structures, not something you could draw a clear outline around, but patterns. Variations in density, regions where gas is slightly more concentrated, areas where molecules are more likely to form. And this is where the idea of hidden structure becomes important, because even though the cloud may appear diffuse when viewed as a whole, it is not uniform. There are differences from one region to another. Some parts are denser, some are warmer, some are more shielded from radiation, and those differences matter. They determine where molecules can form and survive. They influence how gas moves. They shape the overall behaviour of the system. Now, if we gently zoom out, the picture becomes even more interesting. Because the cloud surrounding APM 08279 plus 5255 is not isolated from the rest of its galaxy. It is connected. Gas flows into the region from larger scales. Material is drawn toward the central black hole. At the same time, energy and matter are pushed outward. So the cloud becomes part of a larger cycle. Matter moving inward, feeding the quasar. Energy moving outward, shaping the surrounding environment. And within that cycle, the cloud is constantly evolving. Now, here's something quietly fascinating. Even in such an energetic system, there can be regions that are relatively stable. Not perfectly still, but stable enough for certain processes to occur over long periods. These are the regions where molecules like water can exist, where density is high enough, where radiation is not overwhelming, where conditions allow for the persistence of chemical structures. And those regions are not always obvious. They don't stand out visually. They are hidden in the sense that we only detect them through careful analysis, through spectroscopy, through the patterns in light we talked about earlier. Now let's take a moment to imagine what this might look like if we could somehow map it out, not with our eyes, but with instruments that can detect different wavelengths. You might see a broad extended cloud glowing faintly in infrared or radio wavelengths. Within that cloud you would notice variations, brighter regions, darker regions, areas where certain molecules are more concentrated. And if you could overlay all of that information, you would begin to see a kind of structure, not a solid shape, but a network, a distribution of gas and molecules that forms patterns across space. And within that network, the water exists. Not evenly spread, but concentrated in certain regions, part of the overall structure, influenced by everything around it. Now there's another layer to this that's worth considering: dust. In addition to gas, these clouds contain tiny solid particles, grains of material made of elements like carbon, silicon, and oxygen. These dust grains play an important role in chemistry. They provide surfaces where molecules can form more easily. Atoms can stick to them, meet other atoms, and combine. Water, for example, often forms on the surfaces of dust grains in colder regions. Then when those grains are heated, the water can be released back into the gas phase. So the presence of dust adds another dimension to the structure. It's not just gas moving through space, it's gas interacting with solid particles, forming and reforming molecules over time. Now bringing this back to the idea of an ocean, the comparison becomes a little clearer, but also more nuanced. On Earth, an ocean is a continuous body of liquid. In space, the ocean is part of a cloud, a structure made of gas and dust, with variations and patterns rather than a uniform body. So instead of a flat surface, you have a three-dimensional environment. Instead of waves, you have flows of gas. Instead of currents driven by wind and rotation, you have motion driven by gravity and radiation. And within all of that, the water is distributed. Now, there's something quietly important about recognizing these hidden structures, because they remind us that space is not just empty, it is filled with matter, even if that matter is difficult to see, and that matter organizes itself in ways that are shaped by the forces at work: gravity, radiation, motion, all interacting to create patterns, and those patterns are what we study. Understanding the structure of the cloud leads us to think about the forces that shape it more directly. We've mentioned gravity and radiation, but there's more to explore there. How do these forces interact? How do they influence the motion of gas? And how do they maintain the balance that allows such a vast reservoir of water to persist? Nothing in this region stays still for very long, not in the way we usually think of stillness at least. There are no quiet, unmoving surfaces, no stable ground to stand on, no fixed reference point where you could say, this is at rest. Instead, everything is part of an ongoing flow, shaped by forces that never quite switch off, and at the centre of it all, quietly but relentlessly, is gravity. The gravity of the supermassive black hole inside APM 08279 plus 5255. Now gravity is something we experience every day, but usually in a very gentle, predictable way. It keeps us on the ground, holds the oceans in place, guides the motion of the moon and the planets. It feels steady, constant, almost background-like. But when you scale gravity up to something tens of billions of times the mass of the Sun, it stops feeling like a background effect. It becomes the dominant influence. Everything in the surrounding region responds to it. Gas, dust, molecules, all of it is pulled inward, not all at once, not in a straight line, but gradually, following paths shaped by motion and angular momentum. So instead of falling directly toward the center, the material begins to orbit, and as it orbits, it spirals, slowly moving inward, forming the accretion disk we talked about earlier. Now here's where energy begins to enter the picture in a more visible way. Because as gas spirals inward, it doesn't just move, it interacts. Particles collide, they compress, they heat up, and that heating turns into radiation. Light, X-rays, ultraviolet energy, all being released as the material loses energy and moves closer to the black hole. So gravity pulls inward, and energy is released as a result. But the story doesn't end there, because that energy doesn't just disappear, it flows outward. Radiation pushes against the surrounding gas. In some cases it drives powerful winds, streams of material moving away from the center at high speeds. So now you have two directions of influence, gravity pulling inward, energy pushing outward. And between those two, the system finds a kind of balance, not a perfectly stable balance, not something that remains unchanged, but a dynamic one, a constant negotiation between forces. Now let's bring the water into this picture, because the water molecules are part of this flow. They are carried along with the gas. They move inward, outward, and sideways depending on the local conditions. There is no single direction, no single motion. Instead, there are layers of movement, some gas falling toward the black hole, some being pushed away by radiation, some orbiting at different distances, moving at different speeds, and within all of that the water exists, not as a fixed ocean, but as part of a constantly shifting system. Now, there's something quietly interesting about this, because even though everything is in motion, the overall structure persists. The reservoir of water remains. The cloud does not simply disperse or collapse completely, which means that, on larger scales, the system maintains its shape, even though on smaller scales, everything is changing. This is one of those ideas that feels a little counterintuitive at first. How can something be both stable and constantly moving? But we actually see similar patterns in other systems. On Earth, for example, the atmosphere is always in motion. Winds blow, air circulates, temperatures shift. And yet, the atmosphere as a whole remains. It doesn't disappear, it doesn't collapse, it continues to exist as a system. In a similar way, the region around APM 08279 plus 5255 maintains its structure, even as its components are constantly moving. Now let's look a little more closely at energy. Because energy here is not just something that is present, it's something that is being continuously generated and transferred. The accretion disk releases enormous amounts of energy as matter falls inward. That energy travels outward, interacting with the surrounding gas. Some of it heats the gas, some of it excites molecules, causing them to emit radiation. Some of it drives motion, pushing material away from the center. So energy becomes a kind of connecting thread, linking the central black hole to the outer regions, influencing how gas behaves at different distances, and this has direct consequences for the water, because the presence of energy affects temperature, it affects density, it affects whether molecules can form or survive. Too much energy, and the water molecules break apart. Too little, and the gas may cool and condense in different ways. But in this region, the energy is distributed in such a way that water can persist. Which brings us back to that idea of balance again. Not perfect balance, but a workable one. Now, there's another force at play here as well, though it's often less obvious. Momentum. The gas surrounding the black hole is not starting from rest. It already has motion, and that motion influences how it behaves as it interacts with gravity. Because of angular momentum, gas tends to form disks rather than collapsing directly inward. It spreads out, rotates, and gradually transfers energy and momentum as it moves. This is why the accretion disk forms, and it's also why the surrounding cloud has structure. Different regions move at different speeds. Some rotate faster, some slower, some move inward, some outward. And these differences create patterns. They create the hidden structures we talked about earlier. Now, let's take a step back and look at the bigger picture again. You have gravity pulling material inward. You have energy being released and flowing outward. You have motion in multiple directions, driven by both of those forces. And within that system, you have a vast cloud of gas containing water vapor, all of it interacting, all of it changing, and yet over time maintaining a kind of overall stability, which is what allows us to observe it. Because if the system were too chaotic, if everything changed too quickly, or dispersed too completely, the water might not be detectable. It might not persist long enough for us to see it, but instead, the conditions allow it to remain. Now, there's something quietly remarkable about that, because it shows that even in one of the most energetic environments in the universe, there can be patterns, there can be structure, there can be persistence, not in the sense of stillness, but in the sense of continuity. And that continuity is what makes the idea of a cosmic ocean possible. Not because the water is calm or stable in the way we're used to, but because it exists as part of a system that, as a whole, continues over long periods. Now, as we let that idea settle, there's a natural question that begins to form, because we've talked about motion, we've talked about energy, we've talked about gravity, but there's another aspect of this environment that adds an extra layer to everything, something that doesn't just affect motion, but affects time itself. There's a quiet assumption we carry with us almost all the time. That time moves the same way everywhere. Seconds pass, minutes follow, hours unfold, all at a steady, reliable pace. You don't usually notice it changing, and you don't expect it to behave differently depending on where you are. But that assumption only really holds in places like Earth, where gravity is relatively gentle and space is not too distorted. Near something like APM 08279 plus 5255, that quiet certainty begins to shift. Not dramatically in a way you could immediately feel, but fundamentally in the way time itself is woven into the structure of space. To understand this, it helps to move slowly and build the idea step by step. Because time, in modern physics, is not separate from space. They are part of the same thing, space-time. And when something very massive is present, like the supermassive black hole at the centre of this quasar, it doesn't just pull on objects, it curves space-time itself. Now imagine placing a heavy object on a stretched fabric. The fabric bends. Anything moving nearby follows that curve. That's a common way to picture gravity. But what's often left out of that image is that time is part of the same fabric. So when space-time bends, time changes too. It slows down. Not in a way that feels different locally, but in a way that becomes noticeable when compared to regions farther away. This effect is called gravitational time dilation, and while it exists everywhere, it becomes much more significant near extremely massive objects. So near the black hole in APM 08279 plus 5255, time does not pass at the same rate as it does here on Earth. Closer to the black hole, time moves more slowly. Farther away, it moves more quickly. Now, this doesn't mean that if you were somehow there, you would feel time slowing down. Your own processes, your thoughts, your perception would all move at the same pace from your perspective. But if someone far away were observing you, they would see things differently. They would see your clock ticking more slowly, your movements unfolding more gradually. Now let's gently connect this idea to the environment we've been exploring. The region around the quasar is not a single distance from the black hole. It spans hundreds of light years, which means different parts of it experience slightly different gravitational effects. Closer regions are more strongly influenced, farther regions less so. So within this vast cloud of gas and water vapour, time is not entirely uniform. There are subtle differences in how it flows, not extreme enough to create dramatic contrasts across the entire region, but present nonetheless, and that adds another layer to the system, because now, in addition to motion, energy and structure, we also have variations in time. Now let's take a moment to imagine how this interacts with everything else. Gas is moving inward, radiation is pushing outward, molecules are forming and breaking apart, and all of these processes are unfolding over time, but that time is not identical everywhere. So the rate at which things happen can vary slightly depending on where they are relative to the black hole. Closer in, processes might appear slower from an outside perspective. Farther out, they might appear faster. Now, in practical terms, these differences are subtle across the larger cloud. But near the innermost regions, close to the accretion disk, the effects become more pronounced. And this is where the idea becomes particularly interesting. Because near the edge of the black hole, near the event horizon, time slows down dramatically. From the perspective of a distant observer, it can appear as though time nearly stops. Objects falling toward the black hole seem to slow down more and more, never quite crossing the boundary, at least in terms of what we can observe. But from the perspective of the object itself, the fall continues. Time feels normal, which creates a kind of dual perspective. Two different ways of describing the same event depending on where you are. Now bringing this back to the larger environment, we begin to see that the quasar is not just a place of intense energy and motion, it's also a place where the flow of time itself is shaped by gravity, and that adds a quiet depth to everything we've been discussing, because it means that the processes happening there are not just different in scale, they are different in how they unfold. Now there's another aspect of time that's worth considering here, the time we use to describe these objects. When we say that the light from APM 08279 plus 5255 has taken billions of years to reach us, we are already dealing with a kind of layered time. The time when the light was emitted, the time it took to travel, the time at which we observe it. All of these are connected, but not identical. So when we think about what is happening now at the quasar, it becomes a little more complicated. Because the now we observe is actually the distant past, and the actual present state of the quasar is something we cannot see directly yet. Its light has not reached us. So even without considering gravitational effects, time is already layered in our observations, and when you add in the effects of space-time curvature, the picture becomes even more intricate. Now, instead of trying to resolve all of that complexity at once, it helps to settle into a simpler perspective. Time near the quasar is shaped by gravity. It flows differently depending on distance from the black hole, and everything we observe is part of a long journey through both space and time, which means that when we talk about the cosmic ocean, we are not just describing a structure in space, we are describing something that exists across time as well, a system that has evolved over billions of years, a system we observe as it was in the distant past, and a system where time itself is influenced by the very forces that shape everything else. Now there's something quietly humbling about that, because it reminds us that even something as familiar as time is not fixed. It can stretch, it can slow, it can vary depending on where you are. And in places like this, those variations become part of the story. Once you start thinking about time in this way, it becomes tempting to imagine what it would be like to experience this environment more directly. Not just to observe it from afar, but to move through it, to follow the path of gas and light, to trace the structure of this vast ocean as it exists around the quasar. And while that's not something we can do physically, it is something we can explore in a more imaginative way. A kind of guided journey, built from everything we've learned so far, where we gently step into the environment and see how it might feel to be there. Let's approach this slowly, because the idea of travelling to something like APM 08279 plus 5255 is not something that fits easily into everyday thinking. Not because it's impossible to imagine, but because the scale, the time, and the conditions involved are so far removed from anything we experience that the mind needs a moment to adjust. So instead of jumping straight there, it helps to begin somewhere familiar. Picture yourself leaving Earth, not in a rush, not in a dramatic launch, but gradually, as if distance is something you can ease into. The planet grows smaller behind you. The atmosphere fades into black. The moon becomes a distant companion, then a point, then something you can no longer distinguish from the rest of the sky. You pass beyond the familiar structure of the solar system. The sun, once dominant, begins to look like just another star among many. And then, slowly, you leave even that behind. Now, in reality, such a journey would take far longer than a human lifetime, even at speeds far beyond what we can currently achieve. But here, we're not bound by those limits. This is a guided way of thinking, a way of placing yourself gently into the larger picture. So the journey continues. Stars begin to thin out as you move away from the denser regions of the Milky Way. The galaxy itself becomes something you can see from the outside, a vast, luminous structure stretching across space, and beyond it, more galaxies, some faint, some bright, each one containing billions of stars, each one part of the larger structure of the universe. Now, as you move farther still, the distances become harder to grasp. Millions of light years pass, then billions. The universe around you begins to look different, not because the objects themselves change, but because you are moving into regions where the light you see comes from earlier and earlier times. You are, in a sense, moving backward through cosmic history. And eventually, somewhere in that vastness, you approach the region where APM 08279 plus 5255 exists. At first, it doesn't look like much, just a point of light, slightly brighter than others. But as you draw closer, the nature of that light begins to change. It becomes more intense, more concentrated. Not just a star-like point, but a source of energy that seems to extend outward. And as you continue, the surrounding environment begins to reveal itself. Not as a solid structure, but as a vast, diffuse region of gas, a cloud, or more accurately, a collection of clouds, overlapping, interacting, forming patterns that are difficult to fully take in at once. There is no clear boundary where you can say, this is where it begins. Instead, the density gradually increases. The space around you becomes slightly less empty, still incredibly sparse by Earth standards, but noticeably different from the deeper voids you passed through earlier. Now, this is where the idea of the ocean begins to take shape, not as something you see directly, but as something you understand is present. Water vapor spread across this enormous region, mixed with other gases, moving slowly, almost imperceptibly. If you had instruments, they would detect it. They would show the signatures we talked about earlier, but to your senses it would remain invisible, and yet you would know it's there, part of the environment. Now, as you move deeper into this region, the influence of the quasar becomes more apparent. Radiation increases, not something you would feel as warmth in the usual sense, but something your instruments would register as energy. The closer you get, the more intense it becomes, and with that intensity, the motion of the gas becomes more noticeable, not in the form of winds you can feel, but in the shifting patterns of the cloud, gas flowing inward, other gas being pushed outward, everything part of a larger system driven by gravity and energy. Now somewhere ahead, though you never see it directly, lies the black hole, the centre of all this activity. You cannot approach it safely, not even close, but you can sense its presence through everything around it. The way gas moves, the way light behaves, the way the environment is structured. And as you remain at a distance, observing rather than approaching, you begin to notice something else. Scale, the sheer extent of the region. Even as you move through it, even as you try to follow its structure, it continues to stretch beyond what you can easily grasp. Hundreds of light years, distances that, even in this imagined journey, feel vast, and within all of that the water remains, not gathered, not concentrated, but present. Now, there's something quietly different about experiencing it this way, even in imagination, because instead of thinking in numbers, you begin to sense the proportions, the emptiness between particles, the vast distances between denser regions, the subtle gradients of density and energy, and it becomes clear that this ocean is not something you would ever recognize as an ocean if you arrived without context. It doesn't look like one. It doesn't behave like one in familiar ways. But once you understand what is there, the amount of water, the extent of the region, the comparison begins to make sense. Now, let's take a moment to pause within this imagined journey. You're surrounded by a vast invisible structure, gas drifting, energy flowing, time itself shaped by gravity. And somewhere within all of this, molecules of water, the same simple combination of hydrogen and oxygen that exists on Earth, and yet in a form so different that it almost feels like a separate concept. Now, as you begin to pull back, slowly moving away from the region, the intensity fades, the radiation decreases, the cloud becomes less dense, and eventually the quasar returns to being just a distant point of light again, a bright beacon in the darkness, and the ocean, once something you were moving through, becomes something inferred once more, a concept built from observation and understanding. Now there's something gently grounding about that transition, because it mirrors how we actually experience these objects, from far away, through light, through data, through careful interpretation. We don't travel there, we don't move through those clouds, but we build a picture, step by step, layer by layer, until something that was once completely unknown begins to take shape. And as that picture settles, there's a natural shift in perspective. Because after imagining such a journey, after placing yourself even briefly in that environment, it becomes easier to step back and ask a broader question. Not about what it feels like to be there, but about what it means, what they add to our understanding, and how they change the way we think about the universe as a whole. It's easy, at first, to place a discovery like this into a quiet mental category labelled interesting but distant. After all, APM 08279 plus 5255 is billions of light years away. The ocean surrounding it is not something we can visit, not something that affects daily life, not something that changes how we wake up in the morning or move through the world. So a natural question forms: why discoveries like this matter? And instead of answering that quickly, it helps to slow down and look at it from a few different angles, because the significance of a discovery like this is not found in a single place. It unfolds gradually, one layer at a time. Let's begin with something simple: understanding. Every time we learn something new about the universe, even something distant, we refine our picture of how it works. Not just in that one location, but everywhere. Because the same physical laws apply, the same chemistry, the same interactions between matter and energy. So when scientists detect an enormous reservoir of water around a quasar, they're not just learning about that one system, they're learning about how molecules behave under extreme conditions. They're learning how gas interacts with radiation. They're learning how large-scale structures can form and persist. And that knowledge feeds back into everything else. It helps improve models of star formation. It helps refine our understanding of galaxy evolution. It helps answer questions about how matter organizes itself across the universe. Now, there's another layer to this: expectation. Before discoveries like this, it would have been easy to assume that environments near quasars were too extreme for complex molecules to exist in large quantities, too much radiation, too much energy, too much instability. But the presence of water challenges that assumption. It shows that even in such environments, there are regions where molecules can form and survive, which means that the universe is more flexible than we might have thought, more capable of supporting complexity in places that initially seem unlikely. And that shift in expectation matters, because it changes how scientists approach other questions. It encourages them to look more closely, to consider possibilities that might have been dismissed before. Now let's gently move to another perspective: connection. Water is something deeply familiar. It's part of everyday life. It's part of our own bodies. It's part of the environment we live in. And to find it in such vast quantities, in a place so distant, creates a quiet sense of continuity. The same molecule exists here and there, across billions of light years, across billions of years, which suggests that the universe is not made of entirely separate pieces. It's made of the same building blocks, arranged in different ways, and that connection can be grounding. It places us within the larger picture, not as something separate from the universe, but as part of it. Now, there's also a more practical aspect to consider: techniques. The discovery of water around APM 08279 plus 5255 depends on our ability to detect faint signals, to analyze light with incredible precision, to interpret patterns that are not immediately obvious. And those techniques are not limited to this one discovery. They are used in many areas of astronomy, studying exoplanets, analyzing the atmospheres of distant worlds, understanding the composition of interstellar clouds. So when scientists develop and refine these methods, they are building tools that can be applied elsewhere, tools that expand our ability to explore the universe. Now there's another layer that is a bit more subtle: perspective. When you consider something like the largest known reservoir of water in the universe, it stretches your sense of scale. It reminds you that the universe operates on levels far beyond everyday experience, and that can have an interesting effect. It can make smaller concerns feel a little lighter, not insignificant but placed within a broader context. It can create a sense of space, mentally as well as physically, a feeling that there is more out there, more to explore, more to understand, and that perspective can be valuable in its own quiet way. Now, it's also worth noticing that discoveries like this often lead to more questions than answers. Finding water in such a place raises new possibilities. How common are such reservoirs? Are there even larger ones we haven't detected yet? How does this water evolve over time? What role does it play in the larger system? Each answer opens the door to further exploration, and that process is part of how science moves forward. Not in a straight line, but in a series of steps, each one building on the last. Now, there's one more aspect that's easy to overlook: curiosity. At its core, this kind of discovery matters because it satisfies and at the same time expands our curiosity. Humans have always looked outward, at the sky, at distant objects, wondering what is there. And even when the answers don't have immediate practical applications, they still carry value, because they deepen our understanding. They enrich our sense of the world. They provide a kind of quiet fulfillment. Now, bringing all of this together, the importance of a discovery like this is not tied to a single outcome. It doesn't change one thing in isolation. Instead, it contributes to a larger process: expanding knowledge, refining expectations, strengthening connections, developing techniques, shifting perspective, and encouraging curiosity, all at once. It's tempting to believe that once we understand a few basic rules, the universe should start to feel predictable. Gravity pulls things together, energy flows outward, stars form, shine, and eventually fade. Molecules combine under the right conditions. If you follow those ideas long enough, it might seem like everything should fall into place, like a system that can be fully mapped out with enough patience, and yet, again and again, something unexpected appears. Not because the rules are broken, but because the outcomes of those rules are far more varied than we first imagine. The vast ocean of water surrounding APM 08279 plus 5255 is one of those outcomes. It doesn't contradict anything we know about physics or chemistry. Hydrogen and oxygen can form water. Gas can exist in large-scale clouds. Energy can move through space in complex ways. All of that fits within the framework we understand. But the combination, the scale, the context, that's where the surprise lies. Water, something we associate with calm environments, appearing in enormous quantities near one of the most energetic objects in the universe. And this is not an isolated case. If you look more broadly, the universe is filled with these kinds of unexpected pairings, places where familiar elements appear in unfamiliar settings, objects that behave in ways that don't immediately match our intuition, patterns that only become clear after careful observation. Now, instead of treating that as something unusual, it helps to see it as part of how the universe works. Because the universe does not organize itself according to human expectations. It follows its own rules, and those rules allow for a wide range of possibilities. Let's take a moment to consider how that plays out. When stars form, they don't all follow the same path. Some remain relatively stable for billions of years. Others burn through their fuel quickly and end in powerful explosions. Some systems produce planets, others do not. Even within a single galaxy, the variety is immense. Different environments, different histories, different outcomes. So when we extend that idea to the entire universe, the diversity becomes even more pronounced. And that diversity leads to surprises. Now, there's something quietly important about this, because it means that our understanding is always incomplete, not in a negative sense, but in a way that leaves room for discovery. Each new observation adds to the picture, but also reveals new details that were not previously considered. And that process is ongoing. For example, before quasars were discovered, there was no concept of objects that could outshine entire galaxies. Before gravitational lensing was observed, the idea that light could be bent and magnified in such a way was theoretical. Before molecules were detected in distant regions, space was often thought of as too simple to support complex chemistry. Each of these discoveries expanded our understanding, and each one came with an element of surprise. Now, let's gently connect this back to the ocean around APM 08279 plus 5255. The surprise is not just in the presence of water, it's in the scale, in the idea that something so familiar can exist in such vast quantities in a place so different from Earth. And that kind of surprise has a particular effect. It stretches the way we think. It encourages us to move beyond simple assumptions. Instead of asking, does this fit what we expect? We begin to ask, what else might be possible? Now, there's another layer to this that is a bit more subtle. Because surprises in science are not random. They arise from the same underlying rules, which means that when something unexpected is found, it usually points to a gap in our understanding. Not a flaw in the rules, but a limitation in how we've been applying them. So when astronomers discovered the vast reservoir of water around APM 08279 plus 5255, it wasn't just an interesting fact, it was a prompt. A reason to look more closely at how molecules form and survive in extreme environments. A reason to refine models. A reason to consider new possibilities. And that process continues. Now, let's step back for a moment and look at the bigger pattern. The universe is not just a collection of objects, it's a system of interactions, gravity shaping motion, energy driving change, matter organizing into structures. And within that system, small variations can lead to very different outcomes. A slightly denser region of gas can collapse into a star. A different distribution of material can lead to a planetary system. A particular balance of conditions can allow molecules to accumulate in large quantities. So the universe becomes a place where the same basic ingredients produce a wide range of results. And that range includes things we don't immediately expect. Now, there's something quietly comforting about this idea, because it means that the universe is not limited to a single pattern. It is open-ended, full of possibilities, and that openness is what makes exploration meaningful, because there is always more to find. Now let's bring this back to a more personal perspective for a moment. When you hear about something like the largest ocean in the universe, it might feel distant, abstract, almost separate from everyday life. But at the same time, it can shift the way you think about familiar things. Water on Earth, for example, might start to feel different. not because it has changed, but because you've seen it in a new context. You know now that the same molecule exists in places far beyond our planet, in environments that are completely unlike anything we experience. And that knowledge adds a layer of depth, a sense that even the most familiar things are part of something much larger. Now there's another aspect to this that's worth noticing. Surprises often lead to new questions. Finding water in one place leads to questions about where else it might be found. Understanding one system leads to curiosity about others, and that chain of questions is part of what drives scientific exploration. It's not just about finding answers, it's about expanding the range of questions we can ask. Once you start to see the universe as a place of ongoing discovery, a place where familiar ideas can appear in unexpected ways, it leads to a broader reflection, not just on specific objects, but on the nature of the universe itself, its scale, its complexity, its tendency to combine elements in ways that challenge our assumptions. There's a gentle moment that comes after exploring something vast. Not a sharp ending, not a sudden stop, but a gradual return. The kind where your attention slowly shifts from the distant and unfamiliar back towards something closer, something quieter, something easier to hold. And after spending time around APM 08279 plus 5255, after tracing that immense ocean of water stretched across space, that moment begins to take shape. Because as large as that idea is, as far away as it exists, it doesn't stay distant in quite the same way once you've followed it this far. It becomes part of your picture of the universe, something that quietly sits in the background of your thoughts, even as you return to more familiar ground. So let's begin that return slowly. Imagine once more that distant region, not in sharp detail but as a soft impression, a vast cloud, invisible water spread across hundreds of light years, energy moving through it, gravity shaping everything from the center outward, time itself flowing a little differently near the edges of that enormous black hole, and within all of that, something simple. Water, the same combination of hydrogen and oxygen that exists here on Earth. Now, without rushing, allow that image to drift a little farther away, not disappearing, just becoming more distant again. The quasar returns to being a point of light, bright but small from this perspective. The cloud fades into something you can no longer distinguish directly. The ocean becomes an idea once more. Still real, still vast, but no longer something you are actively moving through, and as that happens, your focus begins to shift. Back toward the space around you, back toward the quiet of your own environment, maybe the room you're in, maybe the sound of your own breathing, maybe the steady rhythm of time passing in the way you're used to. There's something interesting about that transition, because even though nothing around you has changed, your perspective has. You've just spent time considering distances measured in billions of light years, structures that stretch across space in ways that don't have direct parallels in everyday life, and yet, here you are, in a much smaller space, with much simpler surroundings, and somehow both of those realities exist at the same time. Now, there's no need to hold on to all of the details, the numbers, the distances, the exact conditions. They can gently fade. What tends to remain is the impression, the sense that the universe is larger than it first appears, more varied, more flexible, capable of combining familiar elements in unfamiliar ways. And that impression doesn't demand anything from you. It doesn't require analysis or effort. It can simply sit there, quietly, in the background. Now, let's bring this a little closer still. Think again about water, not in space, not in distant clouds, but here. A glass on a table, a drop on your hand, the sound of it moving gently. It's something so ordinary that it rarely draws attention. And yet, now you know that the same molecule exists far beyond this planet, in environments that are completely different, in quantities that are almost impossible to imagine. That connection doesn't change the water itself, but it adds a layer of meaning, a sense that even the simplest things are part of something much larger. Now there's no need to hold on to that thought tightly. it can remain soft, just a quiet awareness, the kind that comes and goes without effort. And as your attention settles, you might notice that the pace of everything feels a little slower. Not because time has changed, but because you've stepped back from the need to follow every detail. You've moved from exploration to rest, from curiosity to calm, and that's a natural place to be, because the universe will still be there. APM 08279 plus 5, 255 will still be shining. That vast ocean of water will still exist, far beyond anything we can reach. Nothing about it depends on constant attention. It simply is. And in the same way, you can allow your thoughts to become less focused, less directed, more like that distant cloud drifting, changing gently, without needing to settle on any one thing. Now, if you notice your mind returning to certain ideas, the scale, the distance, the contrast between Earth and that distant region, you can let those thoughts pass through without holding on to them. They don't need to be resolved. They don't need to lead anywhere. They can simply move, like the gas in that cosmic ocean, part of a larger flow. And as that happens, the sense of distance can begin to soften, not because the universe has become smaller, but because you're no longer trying to measure it. You're simply aware that it exists, which is often enough. Now, there's one last gentle shift that tends to happen here. A return not just to your surroundings, but to a quieter state of attention, where the details of the story begin to fade and what remains is a kind of calm, a sense that you've explored something vast and now you're allowed to rest. No need to follow the next question, no need to move to the next idea, just a pause. A space where everything can settle, and if your eyes are closed, or beginning to close, you might notice that it's easier now. Easier to let go of the effort of thinking, easier to drift. In the same way that light drifts across space, in the same way that molecules drift within that distant ocean, quietly, without urgency, without direction, just moving. And as you settle into that feeling, there's nothing more you need to do. The universe continues, vast and complex, and here, in your own space, things can become simple again, calm, steady, and gently fading into rest.